Hello, and welcome back to Sleepy Darwin. Whether you're here to drift off peacefully, to let your mind wander through deep time, or to simply find a gentle escape from the day's worries, you've found exactly the right place. Tonight, we're embarking on a journey that reaches back billions of years to the very moment when chemistry first learned to become biology, when the first uncertain spark of life flickered into existence on our young planet. We'll be searching for traces of that first creature, not in museums or textbooks, but in ancient rocks, molecular clocks, and the quiet chemistry still humming in your own cells. This is a story of chemical fossils, stubborn bacteria, and the beautiful mystery of how something becomes more than the sum of its parts. Before we begin, I have a small favor to ask. If you enjoy these sleepy explorations into life's deepest questions, a like and subscribe would mean the world to me and to every ancient microbe that made your existence possible. Let me know in the comments where you're listening from and what time it island. Are you drifting off in a bustling city or settling down somewhere the stars still shine bright? I hope this isn't too fascinating to keep you awake, but if it is, at least you'll drift off knowing you're connected to every living thing that ever was. So breathe deep, let your thoughts slow, and let's search together for the first brave creature that dared to be alive. Picture yourself settling deeper into your favorite spot tonight. Whether you're nestled under blankets, curled up on a couch, or perhaps walking quietly under the stars. Take a moment to feel the solid ground beneath you, the air moving gently in and out of your lungs. Everything around you feels so permanent, so established, doesn't it? The rocks, the soil, the very atmosphere that cradles our world. But what if I told you that we're about to step backwards through time itself? Back to when none of this existed. Back to when our Earth was so young, so wild, so utterly alien that you wouldn't recognize it as the same planet that now holds you so tenderly? Tonight, we're going to journey together to the very beginning of our story. Not just the beginning of life, but the beginning of the stage where life would eventually dare to make its first appearance. We're traveling back 4.6 billion years, back to an eon that scientists have named, quite poetically, the Hadean. Named for Hades, the ancient realm of fire and shadow, because our early Earth was indeed a world of flames. Imagine, if you will, that Earth keeps a diary. Not in words, of course, but in layers of rock, in the chemistry of ancient minerals, in the whispered stories that isotopes tell when we know how to listen. Tonight, we're going to read this diary backwards, turning page after page, deeper and deeper into the past, until we reach the very first entries, written in fire and chaos and the slow, patient work of gravity. As we flip back through Earth's geological diary, we pass through familiar chapters first. Here's the age of mammals, the time of dinosaurs, the era when the first trees learned to reach for the sky. Further back now, back past the first fish that dared to crawl onto land, past the explosion of complex life in ancient seas, past the first whispers of multicellular organisms. Keep going back with me. Back past the great oxygenation event that painted our skies blue for the first time. Back past the earliest bacterial mats that learned to harvest sunlight. Back, 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 until we reach the most ancient pages of all. Pages that are scarred and burned and tell of a world that seems more like science fiction than the gentle planet we know today. 4.6 billion years ago, our Earth had just finished forming. But forming is such a gentle word for what was actually happening. Picture instead a cosmic construction site where the workers are asteroids the size of mountains, where the tools are gravity and heat and unimaginable violence, where the blueprints are being rewritten with every collision. This wasn't the slow, measured construction of a cathedral. This was more like, have you ever watched a child having a complete meltdown? The kind where toys go flying, where nothing stays in its proper place, where chaos seems to feed on itself and grow ever more intense. Now imagine that tantrum, but instead of a child, it's an entire planet. Instead of toys, it's molten rock flying through space. Instead of tears, it's the slow, inexorable pull of gravity, gathering dust and debris and ice into an ever-growing ball of cosmic fury. The early Earth was molten, not just warm, not just hot, but molten. Picture the most liquid thing you can imagine. Maybe honey flowing from a jar, or water cascading over stones in a stream. Now imagine that, but it's rock. Liquid rock. glowing orange and red and yellow like the heart of a furnace, flowing and churning and never, ever still. There was no solid ground to stand on, no oceans to reflect the light of the young Sunday, no atmosphere as we know it today. Just a thick, choking blanket of steam and carbon dioxide and gases that would be poison to anything we might recognize as alive. The sky, if you could call it a sky, was a roiling mass of clouds so dense that no sunlight could penetrate to the surface. And the bombardment. Oh, the bombardment. You see, the early solar system was still cleaning house. All around our young sun, countless chunks of rock and ice and metal were still finding their places, still following the ancient dance of gravity. Many of them didn't find a stable orbit. Instead, they fell. They fell toward Mercury, toward Venus, toward Mars, and they fell toward Earth. Some were pebbles, some were boulders, some were mountains flying through space at speeds that would make a bullet seem lazy. When they struck our molten world, they didn't just create craters. They created explosions that could melt continents, that could boil away entire oceans' worth of water vapor, that could knock our planet's rotation askew like a cosmic pool ball. This period of cosmic bombardment has a name that sounds almost gentle, the Late Heavy Bombardment, but there was nothing gentle about it. For hundreds of millions of years, our Earth was essentially being rebuilt with every major impact. Any surface that managed to cool and solidify would be melted again by the next asteroid strike. Any atmosphere that tried to form would be blasted away into space. Any water that condensed from the eternal clouds would immediately boil back into steam. It was a world of constant becoming, never being. A world where the only constant was change, and change of the most violent kind. And yet, and this is the beautiful part, even in all this chaos, even in this cosmic tantrum, the seeds of possibility were being planted. Every asteroid that struck our world brought with it the building blocks of complexity: carbon from the depths of space, water ice from the outer solar system, organic molecules formed in the cold reaches between the stars. The very violence that seemed to prevent life was actually delivering life's raw materials, special delivery from the cosmos. It's humbling, isn't it? To think that you and I, sitting here peacefully tonight, are made of atoms that survived that bombardment, that traveled billions of miles through space, endured impacts that could vaporize mountains, and somehow held on to their chemical stories long enough to eventually become part of a world where quiet moments like this one are possible. But even the most violent cosmic tantrums eventually exhaust themselves. Even the most chaotic construction sites eventually run out of debris to throw around. And so it was with our early Earth, around 4 billion years ago. And isn't it strange how casually we can say 4 billion years ago, as if we're talking about last Tuesday? Around 4 billion years ago, things began to settle down. Not quickly, you understand. This wasn't like flipping a switch from chaos to calm. It was more like, have you ever watched a pot of boiling water slowly cool? How the violent bubbling gradually gives way to gentle movement, then to stillness. The late heavy bombardment was winding down. The largest asteroids had mostly found their final resting places, either on planetary surfaces or in stable orbits around the Sunday. The impacts that still occurred were smaller, less frequent, less catastrophic. For the first time in hundreds of millions of years, Earth's surface could begin to solidify without being immediately melted again. And what a surface it was becoming. Picture a world of volcanic islands rising from a global ocean, not the familiar continents we know today. Those would take billions more years to grow and drift into their current positions. Instead, think of countless volcanic peaks, some tiny, some massive, poking up through the waves like the fingers of some buried giant. The atmosphere was still alien, still poisonous to anything we might call life today. There was very little oxygen. In fact, free oxygen would have been toxic to the kinds of chemistry that was just beginning to experiment with the possibility of becoming alive. Instead, the air was thick with methane, ammonia, hydrogen sulfide, gases that smell like swamps and rotten eggs and industrial accidents. But here's the miraculous thing. For the first time since Earth's formation, the temperature was dropping into a range where water could exist as a liquid, not just as steam, not just as ice, but as the flowing, dancing, ever-changing medium that would become life's favorite playground, the first oceans. Can you imagine witnessing their birth? Picture clouds that have been building for millions of years, clouds so thick and heavy with water vapor that they blot out the sun completely. And then, as the temperature finally drops below the boiling point of water, it begins to rain. But this isn't the gentle rain you might step out into on a spring afternoon. This is rain like the world has never seen before or since. Rain that falls continuously for thousands, perhaps millions of years. Rain that comes down in torrents so heavy they could knock you flat, so constant they reshape the landscape with every passing day. The raindrops sizzle and steam as they hit the still hot volcanic rock. They carve channels and valleys, they fill every depression, they turn the entire world into one vast, shallow sea. And slowly, slowly, the ocean cools from nearly boiling to merely very warm. To temperatures where chemistry can do more than just explode or evaporate. This was our planet's first lullaby, the sound of endless rain finally filling the basins that would become our oceans. The sound of a world settling down after its violent birth, preparing to dream its first dreams of life. And in those warm, shallow seas, chemistry began to dance instead of merely react. Molecules that had been simple started linking together in more complex ways. Carbon chains began forming, breaking apart, forming again in new patterns. The boundary between the purely chemical and the potentially biological started to blur. The stage was set. The theatre of Earth was finally ready for its first performance. The lights had dimmed from the blazing chaos of the Hadean to a warm, steady glow. The orchestra of chemical reactions was tuning up. The audience of rocks and water and atmosphere waited in expectant silence. But there were no actors yet, no living things to walk onto this newly prepared stage. Just chemistry, endlessly creative chemistry, beginning to explore possibilities that had never existed before in the history of our solar system. The transition from the violent Hadean eon to the more stable Archean eon wasn't marked by any single dramatic event. It was more like watching a storm gradually pass. The thunder growing more distant, the lightning less frequent, the wind settling from a howl to a whisper. By about 3.8 billion years ago, our planet had achieved something it had never known before. Stability. Not the absolute stability of a dead world, mind you. Earth was still young, still restless, still actively volcanic and seismically alive, but it was stable enough for experiments, stable enough for chemistry to try new combinations without being immediately undone by the next asteroid impact or volcanic eruption. And chemistry, it seems, is endlessly curious. Given enough time and the right conditions, it will try everything. Every possible combination, every potential reaction, every conceivable way that atoms can link hands and dance together. Most of these experiments lead nowhere, dissolving back into simpler components as quickly as they formed. But some of these chemical experiments would prove to have staying power. Some would discover the secret of making copies of themselves. Some would learn to grow, to change, to respond to their environment. Some would take the first tentative steps across the invisible line that separates chemistry from biology. So what exactly are we searching for as we peer back through these impossibly ancient mists of time? What would the first living thing have looked like if we could somehow travel back and observe it with our own eyes? This is where we need to let go of almost everything we associate with the word creature. Forget about eyes that can see, hearts that can beat, brains that can think. Forget about fur or feathers or scales, about legs for walking or wings for flying or fins for swimming. The first living thing would have had none of these features. In fact, you wouldn't have been able to see it at all, not with your naked eyes. It would have been microscopic, smaller than the tiniest bacterium living today. No definite shape, no hard edges, just a tiny bubble of organized chemistry floating in the warm, ancient sea. But what a bubble it would have been. What a profound miracle hiding in something so small you'd need a powerful microscope to even know it was there. You see, this first creature, let's call it that, even though it was unlike any creature we know, this first living thing would have been defined not by what it looked like, but by what it could do. And what it could do was something that no purely chemical reaction had ever done before. It could make copies of itself. Now, making copies might not sound particularly impressive at first. After all, crystals can make copies of themselves in a sense. adding new layers of atoms in the same pattern as the old ones. Ice crystals do this when they form those beautiful patterns on your winter windows. Salt crystals do it when seawater evaporates and leaves behind geometric deposits. But the copying that this first living thing could do was different. It wasn't just adding more of the same material in the same pattern. It was creating entirely new individuals, each one capable of growing, changing, and making copies of its own. Imagine it like this. Suppose you had a very special kind of cookbook. Not only could this cookbook tell you how to make a delicious meal, but somehow, in the process of following its recipes, you would create a brand new copy of the cookbook itself. And that new cookbook could then be used to make more meals and more cookbooks, and each of those cookbooks might have tiny variations. Maybe a slightly different ingredient here, a modified cooking time there. That's what the first living thing could do. Except instead of cookbooks and meals, it was working with molecules and chemistry. It carried within itself the instructions for making another version of itself. And in the process of following those instructions, it would create not just the raw materials for life, but the information patterns that could guide future generations. But here's where it gets even more beautiful. This first creature wouldn't just make perfect copies. It would make copies with tiny differences, tiny variations, tiny experiments in being alive. Some of these variations would be improvements, making the new creature better at surviving in the ancient ocean. Others might be neutral changes that didn't help or hurt. Still, others might be mistakes that made survival harder. And for the first time in the history of our planet, these differences would matter in a new way. The variations that helped with survival would be more likely to make copies of themselves. The variations that hindered survival would be less likely to reproduce. And slowly, the population of these first living things would begin to change, to improve, to explore new ways of being alive. This is evolution in its most basic form, copying with variation, where some variations survive better than others. It's the engine that would eventually lead from that first tiny bubble of organized chemistry to the vast diversity of life we see around us today, to the bacteria that live in boiling hot springs and the fish that swim in the deepest ocean trenches, to the trees that reach toward the sky and the fungi that connect forest floors in vast underground networks. To you, sitting here tonight, your brain processing these words, your heart beating steadily, your cells carrying on thousands of chemical reactions every second, all of it traceable back to that first moment when chemistry learned to copy itself with creative variations. We're looking for the spark between chemistry and biology, the moment when matter became life, the instant when the universe became capable of wondering about itself. And the beautiful, frustrating truth is that we may never find it. Not as a specific moment, not as a particular creature, not as a single aha discovery that we can point to and say, there, that's when life began. The transition from non-living chemistry to living biology was probably gradual, probably messy, probably involved countless false starts and failed experiments. It might have happened not once, but many times, in many different ways, until finally one particular approach to being alive proved so successful that it became the ancestor of everything living today. But even if we never find that exact moment, that specific first creature, we can still trace its influence. We can see its legacy in every living thing around us. We can recognize its innovations in the way our own cells operate. We can honor its ancient courage in our own curiosity about the world. Every time you take a breath, you're using molecular machinery that can trace its ancestry back to that first living thing. Every time your body heals a cut or fights off an infection, you're benefiting from evolutionary innovations that began with that first creature's ability to copy itself with variations. Every time you learn something new or adapt to a challenging situation, you're participating in the same fundamental process that allowed life to begin and flourish on our young planet. So as we continue our journey together tonight, searching through the deep history of our world for traces of that first living thing, remember that we're not just looking for something that existed billions of years ago. We're looking for the beginning of a story that includes us, that flows through us, that continues in us. We're looking for our deepest ancestor, the first member of the family of life to which we all belong, the original pioneer who took chemistry's first brave step into the unknown territory of being alive. And in a sense, we don't need to find it to know it, because it's here, right now, in this moment. It lives on in every heartbeat, every breath, every thought. The first creature that ever lived isn't just an ancient mystery to be solved. It's the foundation upon which this very moment of wonder and curiosity is built. In our next chapter, we'll explore why finding direct evidence of this first life is so beautifully, frustratingly difficult. We'll discover why the Earth, for all its careful record-keeping, has allowed some of its most precious early stories to fade away. We'll learn about the challenge of reading whispers that are billions of years old. But for now, just rest with this image. Somewhere in the warm seas of the early Earth, in waters that sparkled under an alien sky, chemistry was getting ready to become life. The stage was set, the conditions were right, and the most important story in the history of our planet was about to begin. Imagine trying to find evidence that your great-grandmother once lived in an old house, but you're not allowed to look for photographs, letters, or any obvious traces. Instead, you must search for the faintest impressions, perhaps the way sunlight faded one corner of a windowsill where she liked to sit, or a barely perceptible wear pattern on a floorboard where she walked the same path each morning. This is the predicament paleontologists face when searching for Earth's earliest life. The very nature of ancient organisms conspired against their preservation, leaving us to piece together biology's greatest mystery from whispers and shadows. The first life forms were nothing like the charismatic dinosaurs that capture our imagination, or even the sturdy shells and bones that readily fossilize. Early life was ephemeral, soft-bodied, microscopic, and utterly fragile. These pioneering organisms were little more than delicate membranes enclosing chemistry, vulnerable packets of organic molecules that could be destroyed by the slightest disturbance. Consider the irony. The most revolutionary moment in Earth's history, the emergence of life itself, was enacted by creatures so delicate they could barely maintain their own existence, let alone leave lasting monuments to their presence. They were like thoughts made manifest, brief flickers of organization in an otherwise chaotic world. Without bones, shells, or woody tissues, they possessed nothing that could readily transform into stone, nothing that could serve as a geological bookmark marking their place in deep time. Most early life was also microscopic, existing in a realm invisible to the naked eye. While a towering tree or massive dinosaur creates an undeniable presence in the landscape, early microbes lived in dimensions measured in micrometers. Their entire civilizations could flourish and vanish in spaces smaller than the period at the end of this sentence. Even when present in astronomical numbers, their individual forms remained beyond the threshold of easy preservation. These organisms were also shy, in the sense that they inhabited environments that were either hostile to fossilization or prone to later destruction. They thrived in hot springs, deep ocean vents, acidic pools, and other extreme environments where the very conditions that supported their unusual chemistry worked against the preservation of their remains. They were life's pioneers, venturing into territories so harsh and unstable that few traces of their existence could survive the passage of geological time. Fossilization is not the natural fate of dead organisms, it is a rare and miraculous exception. For every creature that becomes a fossil, countless millions decompose completely, returning their constituent atoms to the endless recycling of Earth's chemistry. The process of fossilization requires a perfect storm of conditions, as unlikely and precise as capturing a whisper in stone. First, an organism must die in just the right place. It needs to be quickly buried in sediment before scavengers can scatter its remains or bacteria can complete their work of decomposition. This burial must be gentle enough not to destroy delicate structures, yet rapid enough to outpace decay. The sediment itself must be fine-grained, able to capture minute details like a high-resolution photograph translated into rock. The chemistry must also be perfect. The water percolating through the sediment needs the right pH, the right mineral content, and the right temperature to gradually replace organic tissues with stone while preserving their original form. Too acidic, and even bones dissolve away. Too basic, and different problems arise. The process is like developing a photograph in a dark room. Every variable must be precisely controlled, or the image disappears. Time adds another layer of complexity. The fossil must survive not just the initial burial and mineralization, but millions or billions of years of geological upheaval. Mountain ranges will rise and fall, continents will drift across the globe, and the very rocks containing the fossil will be subjected to heat, pressure, and chemical assault. Most fossils are destroyed long after their formation, casualties of Earth's restless geological activity. For early life, these already astronomical odds became virtually impossible. Soft tissues rarely fossilize under the best of conditions, and the microscopic scale of early organisms made preservation even more unlikely. It's as if we're trying to preserve whispers in a hurricane, attempting to capture the most delicate traces of existence in a world designed to erase them. The deep time that separates us from life's origins is not just a vast duration, it is an active destroyer of evidence. Every day that passes is another day of chemical weathering, erosion, and geological transformation. The rocks that might have contained fossils of early life have been crushed in mountain-building episodes, melted in volcanic events, dissolved by acidic groundwater, or simply worn away, grain by grain, by wind and rain. Consider the scale of this destruction. In the 3.5 billion years since complex life first appeared, entire mountain ranges have been built and completely eroded away multiple times. The ocean floors, where much early life flourished, have been recycled through the process of plate tectonics, carrying their fossil record down into Earth's interior to be melted and reformed. The ancient rocks that do survive are often so altered by heat and pressure that any fossils they once contained have been transformed beyond recognition. The chemistry of deep time is equally destructive. Even rocks that escape major geological violence are constantly bathed in groundwater that can dissolve away the most resistant materials given enough time. Limestone formations that might have preserved ancient microbes can be completely dissolved by slightly acidic water, leaving behind empty caves where fossil treasures once resided. The very process of diagenesis, the transformation of sediment into rock, often destroys delicate structures through recrystallization and chemical change. Perhaps most frustratingly, some of the best evidence for early life probably dissolved away in the first few million years after the organisms died. Many early life forms likely had characteristics that would have made them easily fossilizable under the right conditions. Perhaps they built delicate mineral structures or lived in environments conducive to preservation. But these traces were so ancient that they succumbed to destruction long before more recent, more familiar life forms appeared on the scene. The result is a fossil record that is not just incomplete, but systematically biased against the very life forms we most want to understand. It's as if someone took the most important pages from the book of life's history and fed them to a fire, leaving us to reconstruct the story from scattered fragments and marginal notes. Despite the overwhelming odds against preservation, early life did leave us some messages written in stone. The most spectacular of these are stromatolites, layered rock structures that represent some of the oldest evidence of life on Earth. These formations are like libraries constructed by ancient microbes, with each layer representing a chapter in the story of early biological communities. Stromatolites form through the activities of cyanobacteria and other microorganisms that build thin mats on the surfaces of shallow waters. These microbial mats trap and bind sediment particles while the bacteria photosynthesize and grow upward toward the light. Over time, this process creates distinctive layered structures that can grow to impressive sizes. Some ancient stromatolites rise several meters high, representing thousands of years of continuous microbial construction. The beauty of stromatolites lies not just in their preservation, but in what they tell us about early life. These structures demonstrate that by at least 3.5 billion years ago, microorganisms had developed sophisticated community behaviors. The bacteria didn't just exist as isolated cells, they formed complex, organized mats that could modify their environment on a grand scale. They had learned to work together, creating structures that were far more durable than any individual organism. Modern stromatolites still form in a few places on Earth, primarily in hypersaline environments like Shark Bay in Western Australia. These living examples give us insights into how their ancient counterparts might have formed and functioned. Watching modern stromatolites grow is like seeing Earth's earliest ecosystems in action, a direct connection to biological processes that have remained essentially unchanged for billions of years. The stromatolite record also tells a story of decline and recovery. After flourishing for billions of years, stromatolites largely disappeared from the fossil record around 1 billion years ago, possibly due to the evolution of grazing organisms that could consume the microbial mats. Their near disappearance marks one of the most significant ecological transitions in Earth's history, the end of the age of bacteria and the beginning of more complex ecosystems. In the remote Pilbara region of Western Australia, some of the Earth's oldest rocks tell an extraordinary story. Here, In formations with names like the Dresser Formation and the Strelly Pool Formation, scientists have discovered what may be the oldest direct evidence of life on our planet, bacterial mats that flourished 3.5 billion years ago when Earth was still a young and violent world. These ancient mats were discovered in rocks that have survived an almost unimaginable journey through deep time. They formed when the Earth was dramatically different from today. The atmosphere contained virtually no oxygen, the sun was dimmer, and the surface was bombarded by asteroids and comets. Yet somehow, in this alien world, life not only existed, but thrived well enough to leave traces that would survive until today. The preservation of these mats is nothing short of miraculous. The bacteria lived in shallow, warm pools that were rich in silica, the same mineral that forms quartz and glass. As the bacteria died, this silica quickly encased their remains, creating a kind of biological glass that preserved cellular details with extraordinary fidelity. Some of these fossils are so well preserved that scientists can still see individual cells and even internal cellular structures. What makes these discoveries particularly remarkable is that they don't just show us that life existed 3.5 billion years ago, they reveal that it was already sophisticated. The bacterial mats show evidence of complex community structures, with different types of bacteria occupying different niches within the same formation. Some bacteria appear to have been photosynthetic, others may have been chemosynthetic, and still others probably played roles in nutrient cycling and waste processing. The study of these ancient mats has also revealed evidence of early chemical warfare between competing bacterial groups, sophisticated responses to environmental stress, and even possible examples of primitive multicellular organization. These weren't simple, primitive life forms struggling to survive. They were complex biological communities with their own ecologies and evolutionary dynamics. Perhaps most amazingly, these Australian fossils have yielded organic molecules that are almost certainly original biological material, actual pieces of organisms that lived 3.5 billion years ago. These molecules provide a direct chemical link to Earth's earliest life, allowing scientists to study not just the structure of ancient organisms, but their actual biochemistry. Even when the organisms themselves don't survive as recognizable fossils, life often leaves behind chemical signatures that can persist for billions of years. These molecular fossils, or biomarkers, are like a perfume that lingers long after the wearer has left the room, subtle but unmistakable evidence of life's former presence. One of the most important of these signatures involves carbon isotopes. Living organisms preferentially use the lighter isotope of carbon, carbon-12, over the heavier one, carbon-13, when they build organic molecules. This biological preference creates a distinctive isotopic signature that can be preserved in ancient rocks long after the organisms themselves have disappeared. When scientists find this signature in ancient sediments, it's strong evidence that life was present, even if no actual fossils can be found. These isotopic signatures have pushed the evidence for life back even further than the oldest fossils. Some rocks from Greenland, dating to 3.8 billion years ago, show carbon isotope ratios that strongly suggest biological activity. If confirmed, this would mean that life appeared on Earth within just a few 100 million years of the planet's formation, remarkably quickly in geological terms. Other chemical fossils include complex organic molecules called biomarkers that are produced only by living organisms. Sterones and hopanes, for example, are molecular fossils derived from steroids and bacterial membrane lipids, respectively. These molecules can survive in rocks for billions of years, providing direct evidence of the types of organisms that once lived there. The discovery of these molecules in rocks over 2.7 billion years old has provided evidence for early eukaryotic life and sophisticated bacterial communities. Sulfur isotopes tell another part of the story. The way living organisms process sulfur creates distinctive isotopic signatures that can reveal information about ancient metabolisms and environmental conditions. Changes in sulfur isotope ratios through time have been used to track the evolution of different metabolic pathways and the changing chemistry of Earth's ancient oceans and atmosphere. Even the minerals in ancient rocks can carry biological signatures. Some minerals form only under conditions created by living organisms, while others show distinctive crystal habits when they form in the presence of biological activity. These mineral signatures can sometimes be detected even when all other evidence of life has been destroyed. The study of these chemical fossils has opened up entirely new ways of searching for ancient life. Scientists can now detect the presence of past life in rocks that show no visible fossils, expanding our ability to trace biology back through deep time. It's as if we've learned to read life's signature in the very atoms of ancient rocks. Every fossil discovery from deep time carries with it a sense of the miraculous. Finding evidence of life that lived billions of years ago is like discovering a pressed flower in the pages of an ancient book, a delicate reminder of beauty and complexity that somehow survived against all odds. Each specimen represents not just a scientific data point, but a profound connection across the vast expanse of geological time. Consider what it means to hold a 3-5 billion-year-old fossil in your hands. The rock you're touching was formed when Earth was less than a quarter of its current age. The life it preserves existed for a span of time longer than the entire subsequent history of complex life on Earth. These organisms lived and died, reproduced and evolved, built communities and responded to environmental changes, all in a world so alien that it might as well have been another planet. Yet despite the immense temporal gulf that separates us from these ancient life forms, there are profound continuities. The same basic chemistry that powered these early organisms still runs in our cells today. The DNA that encoded their genetic information uses the same four-letter alphabet that spells out human genes. The fundamental processes of life metabolism, reproduction, evolution have remained essentially unchanged across billions of years. Each discovery also represents the culmination of extraordinary detective work. Finding and interpreting these ancient fossils requires a combination of geological insight, chemical analysis, and biological understanding that pushes the boundaries of multiple scientific disciplines. The rocks must be collected from remote locations, often requiring expeditions to some of the most inhospitable places on Earth. The fossils themselves are frequently so small and subtle that they can only be seen with powerful microscopes, and so rare that years of searching might yield only a handful of specimens. The interpretation of these fossils is equally challenging. How do you prove that a microscopic structure in a billion-year-old rock is actually a fossil and not just an unusual mineral formation? How do you determine what kind of organism it represents and how it lived? These questions require sophisticated analytical techniques and careful comparison with modern organisms and experimental studies. Perhaps most remarkably, each fossil discovery has the potential to rewrite our understanding of life's history. A single well-preserved specimen can push back the earliest evidence for a particular type of organism by hundreds of millions of years, or reveal unexpected complexity in ancient ecosystems. The discovery of the Gunflint Formation fossils in the 1952 revolutionized our understanding of Precambrian life. More recent discoveries continue to surprise scientists and challenge preconceptions about early evolution. Despite remarkable advances in fossil hunting and analytical techniques, we must acknowledge that some chapters in life's story may be forever lost to us. The very antiquity that makes early life so fascinating also places fundamental limits on what we can know. Some stories, it seems, the Earth simply will not tell. The farther back we look in time, the more severe these limitations become. The oldest rocks on Earth date back only about 4 billion years, but our planet formed 4.6 billion years ago. The entire first 600 million years of Earth's history, the Hadean Eon, is largely missing from the geological record. If life originated during this time, as some scientists suspect, we may never find direct fossil evidence of it. Even within the preserved rock record, the chances of fossilization become vanishingly small as we go further back in time. The delicate early life forms we most want to understand were precisely those least likely to be preserved. We're forced to acknowledge that our view of early evolution is necessarily incomplete and probably biased toward organisms and environments that were most conducive to fossilization. There are also technical limits to what we can extract from the fossils we do find. The processes of fossilization and geological alteration inevitably destroy some information while preserving other details. We can see the shapes of ancient cells, but we cannot directly observe their metabolisms. We can detect the chemical signatures of ancient ecosystems, but we cannot watch their ecological interactions in real time. Perhaps most humbling is the recognition that absence of evidence is not evidence of absence. Just because we haven't found fossils of a particular type of organism in rocks of a certain age doesn't mean those organisms didn't exist. It might simply mean that they haven't been preserved or that we haven't looked in the right places. The history of paleontology is full of discoveries that filled apparent gaps in the fossil record. revealing that the gaps were artifacts of preservation rather than real absences in the history of life. These limitations extend beyond individual fossils to entire ecosystems and evolutionary events. The origin of life itself, perhaps the most important event in biological history, may have left no direct traces that we can recognize. The earliest steps in the evolution of complex cells, the first photosynthetic organisms, the initial colonization of land, all of these crucial transitions might be invisible in the fossil record. Rather than being a weakness, the uncertainty inherent in studying deep time represents one of the most beautiful aspects of scientific inquiry. It reminds us that science is not just about accumulating facts, but about wrestling with the unknown and finding meaning in the face of incomplete information. The gaps in our knowledge are not failures, they are invitations to wonder, to hypothesize, and to continue searching. This uncertainty also teaches us intellectual humility. Despite our sophisticated instruments and analytical techniques, despite our growing understanding of biology and geology, we remain small figures attempting to comprehend processes that operated on scales of time and space that dwarf human experience. The fossil record reminds us that we are recent arrivals in a story that began billions of years before we appeared and will continue long after we are gone. There is something profoundly moving about this confrontation with the limits of knowledge. It connects us to the fundamental human experience of seeking understanding in an incomprehensible universe. The paleontologist searching for microscopic fossils in ancient rocks is engaged in the same essential human activity as the astronomer probing the depths of space, or the physicist exploring the nature of matter and energy. The uncertainty also preserves a sense of mystery and wonder that might otherwise be lost if we knew everything. The gaps in the fossil record leave room for imagination and speculation, for competing hypotheses and ongoing debates. They ensure that the study of early life remains an active, dynamic field rather than a completed catalogue of known facts. Perhaps most importantly, this uncertainty reminds us that scientific knowledge is provisional and evolving. Today's certainties may become tomorrow's misconceptions as new discoveries challenge our current understanding. The history of paleontology is filled with dramatic reversals and unexpected discoveries that forced scientists to completely revise their theories about early life. In our quest to understand life's origins, we sometimes forget that the journey can be as rewarding as the destination. The process of searching for ancient life, the careful examination of rocks, the patient analysis of chemical signatures, the gradual construction of hypotheses, is itself a profound form of engagement with the natural world. Not knowing forces us to be creative, to develop new techniques and approaches, to look at familiar things in new ways. The challenges posed by the sparse fossil record have driven innovations in analytical chemistry, microscopy, geology, and biology. These methodological advances often have applications far beyond paleontology, contributing to our understanding of modern ecosystems, climate change, and even the search for life on other planets. The gaps in our knowledge also create space for interdisciplinary collaboration. Understanding early life requires insights from biology, chemistry, geology, physics, and astronomy. This interdisciplinary approach has led to new synthetic understandings that none of these fields could have achieved alone. The study of early life has become a meeting ground where different scientific traditions come together to address common questions. Moreover, the uncertainty surrounding early life connects us to some of the deepest philosophical questions humans have always asked. Where did we come from? What is life? Are we alone in the universe? These questions may not have simple answers, but the process of pursuing them reveals something essential about human nature, our drive to understand our place in the cosmos. The search for early life also reminds us that science is fundamentally a human activity, shaped by our limitations, biases, and perspectives. The story we tell about early life is not just an objective account of what happened billions of years ago, it is also a reflection of who we are as a species and what we value. Our fascination with origins, our desire to find connections across deep time, our willingness to dedicate careers to studying microscopic fossils, all of these reveal something profound about human consciousness and curiosity. Finally, not knowing everything leaves room for future generations to make their own discoveries and develop their own understanding. The fossil record we study today will be different from the one studied by scientists a century from now. New fossils will be found, new analytical techniques will be developed, and new theoretical frameworks will emerge. The story of early life will continue to evolve, ensuring that each generation can participate in the ongoing human quest to understand our biological heritage. In the end, the fossil problem, the difficulty of finding evidence for ancient life, is not really a problem at all. It is an inherent feature of studying deep time, a reminder of the profound temporal and spatial scales on which life operates. The fragments we do find are all the more precious because of their rarity, all the more meaningful because of the vast silence that surrounds them. They are pressed flowers in the billion-year-old book of Earth's history, delicate reminders of the creativity and persistence of life in the face of seemingly impossible odds. The search for these traces continues, driven by the same curiosity that has always motivated human inquiry into the natural world. With each new discovery, we add another page to the story of life on Earth, even as we remain humbled by how much of that story remains hidden from us. In this ongoing dialogue between the known and unknown, between evidence and interpretation, between wonder and understanding, we find perhaps the most authentic expression of what it means to be human in a cosmos, far stranger and more magnificent than we can fully comprehend. If life were a cookbook, it would surely be the most mysterious recipe collection ever written. The ingredients seem simple enough: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, the basic elements that form life's molecular alphabet. Yet somehow, when combined under the right conditions, these ordinary atoms perform an extraordinary transformation. They begin to organize, to reproduce, to respond to their environment, and ultimately to evolve. They cross the ineffable boundary from mere chemistry to something we recognize as life. But what exactly is this boundary? When does a collection of molecules stop being just a complex chemical system and start being alive? This question has puzzled scientists and philosophers for centuries, and the answer remains beautifully elusive. Perhaps that's because life didn't emerge in a single dramatic moment, like lightning striking a primordial soup, but rather through a gradual transition, a slow dance of molecules learning to work together, to remember, and to persist. The boundary between living and non-living is far more blurred than we might expect. Consider a virus, that microscopic entity that exists in the twilight zone between chemistry and biology. Outside a host cell, a virus is little more than a crystalline package of genetic material wrapped in protein, no more alive than a grain of salt. Yet place it inside the right cell, and it springs into action, hijacking the cellular machinery to reproduce itself with ruthless efficiency. Is it alive? The answer depends on when you ask the question. This ambiguity reveals something profound about life itself. It is not a thing, but a process. Not a state, but a dynamic pattern of organization that emerges from the interactions of countless molecules. Life is what happens when chemistry becomes sufficiently complex and integrated, that it begins to exhibit properties that seem almost magical: self-maintenance, reproduction, adaptation, and evolution. The hallmarks of life that biologists traditionally recognize include metabolism, the ability to harness energy and materials from the environment; reproduction, the ability to make copies of oneself; response to stimuli, the ability to sense and react to changes; growth and development, the ability to increase in size and complexity; and evolution, the ability to change over time in response to environmental pressures. Yet even these criteria prove slippery under close examination. Crystals can grow and reproduce their structure, but we don't consider them alive. Computers can respond to stimuli and even evolve through genetic algorithms, but they remain firmly in the realm of the non-living. Fire consumes fuel, produces waste, responds to its environment, and can even reproduce by spreading to new locations, yet we intuitively know it is not alive. Perhaps the key lies not in any single property, but in the integration and coordination of multiple processes. Life emerges when chemical systems become sufficiently organized that they can maintain their own structure while simultaneously changing and adapting. It's the difference between a whirlpool, which maintains its form through the constant flow of water, and a random turbulence that quickly dissipates. Both involve complex fluid dynamics, but only the whirlpool exhibits the kind of persistent, self-maintaining organization that hints at the deeper principles underlying life. The earliest life forms likely existed right at this boundary, as chemical systems that had begun to exhibit some lifelike properties but lacked others. They were probably not clearly alive or dead by our modern standards, but something in between chemical systems in the process of becoming biological ones. This gradual transition helps explain why the origin of life remains such a challenging puzzle. We're trying to identify a boundary that may never have existed as a sharp dividing line. At the heart of all life lies one of the most remarkable phenomena in the universe: the ability of certain molecules to make copies of themselves. This self-replication is so fundamental to life that it's hard to imagine biology without it, yet it remains one of the most extraordinary processes in nature. It's as if certain arrangements of atoms had learned to look in a mirror and recreate what they saw. DNA, the famous double helix that carries genetic information in most living things, performs this miracle through an elegant molecular ballet. The two strands of the helix are complementary, each serving as a template for the reconstruction of the other. When the time comes for replication, the double helix unwinds like a zipper opening, and each single strand directs the synthesis of its partner. The process is guided by simple chemical rules. Adenine always pairs with thymine, guanine always pairs with cytosine, yet the result is the faithful transmission of information across generations. This base pairing system is both robust and flexible, allowing for the storage of vast amounts of information while providing mechanisms for both fidelity and variation. The sequence of bases along a DNA strand can encode the instructions for building and operating an entire organism, from the simplest bacterium to the most complex multicellular creature. Yet occasional copying errors introduce the variation upon which evolution depends, ensuring that life can adapt and change over time. RNA, DNA's simpler cousin, plays an even more versatile role in the molecular machinery of life. While DNA serves primarily as an information storage device, RNA can both store information and catalyze chemical reactions. This dual functionality makes RNA a remarkable molecular Swiss Army knife, capable of reading genetic instructions, carrying them to the cellular machinery that implements them, and even participating directly in the chemical processes of life. The discovery that RNA can act as an enzyme, a biological catalyst, was one of the most important findings in modern biochemistry. These ribozymes, as they are called, can cut and splice other RNA molecules, facilitate the synthesis of proteins, and even replicate themselves under certain conditions. This versatility has led many scientists to propose that RNA preceded DNA in the evolution of life, serving as both the information storage system and the catalytic machinery in the earliest living things. The molecular ballet of replication is choreographed by a host of protein enzymes that ensure the process occurs with remarkable precision. DNA polymerases read the template strands and add the appropriate complementary bases. Proofreading enzymes check for errors and correct them, and other molecular machines unwind the double helix and manage the complex logistics of copying an entire genome. The result is a replication process that is accurate enough to maintain genetic information across millions of generations, yet flexible enough to allow for the gradual accumulation of beneficial changes. This system of information, storage, and transmission is so sophisticated that it's difficult to imagine how it could have emerged from simpler chemical systems. Yet it must have, somehow, through a process that remains one of the deepest mysteries in the study of life's origins. The answer may lie in understanding how simpler, self-replicating systems could have gradually evolved the complexity we see in modern DNA and RNA. While the drama of genetic replication captures much of our attention, the quiet miracle of metabolism is equally essential to life. Metabolism is the set of chemical processes that extract energy and materials from the environment and use them to build and maintain the structures of living things. It's a controlled fire that burns steadily rather than explosively, channeling the energy of chemical reactions into the work of staying alive. The basic challenge of metabolism is thermodynamic. Living things are highly organized structures that exist in apparent defiance of the universal tendency toward disorder. The second law of thermodynamics tells us that entropy disorder always increases in isolated systems. Yet living organisms seem to swim against this tide, creating and maintaining complex, organized structures from simpler components. The secret lies in understanding that living things are not isolated systems. They constantly exchange energy and materials with their environment. Metabolism can be thought of as a vast network of interconnected chemical reactions, each carefully controlled and coordinated with the others. Some reactions break down complex molecules to release energy, catabolism, while others use that energy to build complex molecules from simpler ones, Anabolism. The cell maintains this network in a delicate balance, ensuring that energy is available when and where it's needed while preventing runaway reactions that could damage or destroy the system. The currency of this metabolic economy is typically ATP, adenosine triphosphate, a small molecule that can store and transfer energy through the breaking and forming of chemical bonds. ATP is like the cash of cellular commerce, providing a standardized way to pay for the energy costs of various biological processes. The cell maintains a constant supply of ATP through various metabolic pathways, ensuring that energy is always available for the work of life. The earliest forms of metabolism were probably much simpler than the elaborate biochemical networks we see in modern cells, but they would have faced the same fundamental challenges. They needed to extract energy from their environment in a controlled way, use that energy to maintain their own structure, and somehow couple these processes together so that the system could persist over time. Some scientists believe that metabolism preceded genetic replication in the evolution of life, creating self-maintaining chemical networks that only later acquired the ability to store and transmit information. Others argue that replication came first, with metabolism evolving to support and enhance the process of copying genetic material. Both scenarios face significant challenges, suggesting that perhaps neither process evolved in isolation from the other. The beauty of metabolism lies not just in its functionality, but in its elegance. The same basic chemical principles that govern metabolism in bacteria also operate in plants, animals, and every other form of life. The fundamental processes of energy transformation, the breaking and forming of chemical bonds, the transfer of electrons, the coupling of energy-releasing and energy-requiring reactions are universal features of living systems. Perhaps the most underappreciated component of life's recipe is the cell membrane, that thin barrier that separates the interior of a cell from its environment. This boundary might seem like a simple structural feature, but it represents one of the most fundamental innovations in the history of life. The creation of a distinct inside and outside, a self and a not-self, an autonomous entity that can maintain its own identity while interacting with the world around it. The cell membrane is not a static wall, but a dynamic, selective barrier that controls what enters and leaves the cell. Made primarily of phospholipids, molecules with water-loving heads and water-fearing tails, the membrane spontaneously organizes into a double layer that provides both stability and flexibility. This lipid bilayer is studded with proteins that serve as gates, pumps, sensors, and communication devices, creating a sophisticated interface between the cell and its environment. The emergence of cell membranes solved several critical problems that would have faced early life. First, it provided a way to concentrate biomolecules in a small space, increasing the likelihood of productive chemical interactions. Without membranes, the organic molecules necessary for life would have been diluted throughout the vast oceans, making complex chemistry virtually impossible. Second, membranes allowed for the development of chemical gradients, differences in the concentration of ions and molecules across the barrier. These gradients can store energy, much like water behind a dam, and this stored energy can be tapped to drive various cellular processes. The ability to create and maintain chemical gradients is essential for many forms of metabolism and is probably one of the earliest energy storage mechanisms used by living systems. Third, membranes provided a way to maintain different chemical environments on either side of the barrier. The interior of a cell can have a different pH, salt concentration, and molecular composition than the external environment, allowing for specialized chemistry that would not be possible in a mixed system. This compartmentalization is essential for the complex biochemical networks that characterize all known life. The formation of the first cell membranes may have been surprisingly straightforward. When certain organic molecules are mixed with water, they spontaneously form membrane-like structures, including small spherical vesicles that resemble primitive cells. These protocells, as they are called, can grow, divide, and even compete with each other for resources, exhibiting some of the basic properties of living systems. However, the transition from simple protocells to true cells with sophisticated membranes and complex interior chemistry remains one of the major unsolved puzzles in the origin of life. The membranes of modern cells are marvels of molecular engineering, precisely controlling the flow of materials and information across the cellular boundary. How such sophisticated systems could have evolved from simpler membrane structures is an active area of research. The invention of cell membranes also had profound evolutionary consequences. Once life became cellular, evolution could act on individual organisms rather than just on molecular systems. This opened up new possibilities for complexity and innovation, ultimately leading to the vast diversity of cellular life we see today. The cell membrane, in a very real sense, made evolution possible by creating discrete units of selection that could compete, reproduce, and change over time. One of the most elegant solutions to the puzzle of life's origins is the RNA world hypothesis, which proposes that early life was based entirely on RNA rather than the DNA-protein partnership we see in modern organisms. This idea emerged from the recognition that RNA is uniquely versatile among biological molecules, capable of both storing genetic information and catalyzing chemical reactions, a combination that could, in principle, support a simple form of life. The RNA world hypothesis addresses one of the fundamental chicken and egg problems in understanding life's origins. Modern cells require both DNA, for information storage, and proteins, for catalysis. But DNA cannot replicate without protein enzymes, and proteins cannot be made without DNA instructions. This circular dependency makes it difficult to imagine how either could have evolved first. RNA potentially solves this problem by combining both functions in a single type of molecule. In an RNA world, these versatile molecules would have served as both the genes and the enzymes of early life. RNA, enzymes, ribozymes, would have catalyzed their own replication, creating self-copying chemical systems that could evolve and adapt over time. Some RNA molecules might have specialized in information storage, others in catalysis, and still others in structural roles, creating a division of labor within an RNA-based ecosystem. The analogy of RNA as a librarian who could also cook dinner captures this remarkable versatility. Unlike the highly specialized molecules of modern cells, RNA could wear many hats, serving simultaneously as information, storage device, enzyme, and structural component. This multifunctionality would have been essential in the early stages of life, when molecular resources were limited and efficiency was paramount. Evidence for the RNA world comes from several sources. First, the discovery of ribozymes demonstrated that RNA can indeed function as an enzyme, something that was once thought to be impossible. Second, many of the most fundamental processes in modern cells, including protein synthesis and some forms of RNA processing, are catalyzed by ribozymes, suggesting that these are ancient processes that have been retained from an earlier RNA-based world. Perhaps most intriguingly, the modern apparatus for protein synthesis, the ribosome, is fundamentally an RNA machine. The actual chemistry of linking amino acids together to form proteins is catalyzed by RNA, not by protein enzymes. This suggests that protein synthesis evolved within an already existing RNA world, with proteins initially serving as accessories to RNA enzymes rather than replacing them. The transition from an RNA world to the modern DNA-RNA protein world would have been gradual and driven by the advantages that specialization could provide. DNA is more stable than RNA and better suited for long-term information storage. Proteins are more versatile catalysts than ribozymes and can perform a wider range of chemical reactions. The evolution of these specialized molecules would have allowed life to become more efficient and more complex, but it would also have created the interdependencies that make modern cells so sophisticated yet so vulnerable. Despite its elegance, the RNA world hypothesis faces significant challenges. RNA is a complex molecule that would have been difficult to synthesize under early Earth conditions. RNA is also relatively unstable, especially at the high temperatures that may have characterized early Earth. These problems have led some scientists to propose that an even simpler world preceded the RNA world, perhaps based on peptides, lipids, or mineral surfaces. The origin of life presents us with several chicken and egg problems that highlight the deep interconnectedness of biological systems. The most famous of these involves the relationship between genetic information and the machinery needed to express that information. Modern cells store their genetic instructions in DNA, but these instructions are meaningless without the complex protein machinery needed to read them, copy them, and implement them. Yet this protein machinery cannot exist without the genetic instructions that specify how to build it. This circular dependency is not just a theoretical problem, it points to a fundamental feature of life that makes its origin seem almost miraculous. Living systems are characterized by what biologists call irreducible complexity, meaning that they require multiple interdependent components to function properly. Remove any essential component, and the entire system fails. This raises the profound question of how such integrated systems could have evolved gradually from simpler precursors. The traditional approach to this problem has been to ask which component came first: metabolism or replication, information or chemistry, the chicken or the egg. Proponents of a metabolism first scenario argue that self-maintaining chemical networks could have emerged before the ability to store and transmit genetic information. These networks would have been able to grow and reproduce their chemical organization without relying on a genetic code. Supporters of a replication-first scenario, including advocates of the RNA world hypothesis, argue that information, storage, and transmission were the primary innovations that made life possible. In this view, metabolic networks evolved later to support and enhance the basic process of genetic replication. The ability to make copies of molecular information was the crucial breakthrough that allowed chemical systems to evolve and become more complex over time. However, a growing number of scientists are beginning to question whether this either-or approach is the right way to think about life's origins. Perhaps the chicken and egg problem is a false dilemma that arises from our tendency to think about complex systems in terms of simple, linear causation. Real biological systems are characterized by networks of mutual causation, where each component both influences and is influenced by the others. This suggests that life might have emerged not from a single breakthrough, but from the gradual co-evolution of multiple, interdependent processes. Metabolism and replication, information and chemistry, structure and function, all of these may have evolved together, each enabling and being enabled by the others. Life, in this view, was not an invention, but an emergence, not a moment, but a process. This perspective is supported by recent research into what scientists call systems chemistry, the study of how complex chemical networks can exhibit properties that are greater than the sum of their parts. These networks can display spontaneous organization, self-maintenance, and even primitive forms of evolution, suggesting that the boundary between chemistry and biology may be more gradual than previously thought. The beauty of this systems approach is that it transforms the chicken and egg problem from a frustrating paradox into an opportunity for deeper understanding. Instead of trying to identify the first component of life, we can explore how different chemical processes might have become integrated into the self-maintaining, self-reproducing systems we recognize as living. The question changes from what came first to how did everything come together? One of the most profound insights emerging from modern research into life's origins is that life may have been a community project from the very beginning. Rather than arising from a single self-replicating molecule or a single metabolic network, life may have emerged from the interactions and cooperation of multiple chemical systems, each contributing different capabilities to the emerging whole. This community perspective challenges the traditional image of early life as a solitary struggle for existence, a molecular battle of all against all in which only the fittest survived. Instead, it suggests that cooperation and mutualism were fundamental features of life from its earlier stages. The first living systems may have been confederations of specialized components, each dependent on the others for survival and success. Evidence for this community model comes from several sources. Modern cells are themselves communities of cooperating molecular systems. Genetic replication machinery works together with metabolic networks, which work together with structural systems like membranes and cytoskeletons. None of these systems can function in isolation. They require the integrated cooperation of all the others. Even more striking is the fact that modern cells contain clear evidence of ancient community relationships. The organelles that power plant and animal cells, chloroplasts and mitochondria, are actually the descendants of bacteria that were incorporated into early eukaryotic cells billions of years ago. These organelles retain their own DNA and reproduce independently, yet they are fully integrated members of the cellular community. This arrangement, known as endosymbiosis, demonstrates that cooperation between different forms of life has been a major driver of evolutionary innovation. The community model also helps explain some of the chicken and egg problems that plague other theories of life's origins. If life emerged from the cooperation of multiple chemical systems, then there was no need for a single system to have all the capabilities of life from the beginning. One system might have specialized in information storage, another in catalysis, and another in maintaining boundaries and compartments. Each system could have been relatively simple, but their cooperation could have produced emergent properties that characterized life as a whole. This perspective also suggests that the search for life's origins should focus not just on individual molecules or reactions, but on the networks of interactions that could have given rise to biological organization. The key questions become: how do chemical systems learn to cooperate? What conditions favor the emergence of mutually beneficial relationships? How do networks of interacting systems develop the stability and complexity we associate with life? Recent research in systems chemistry and network theory is beginning to provide answers to these questions. Scientists have discovered that certain types of chemical networks naturally evolve cooperative relationships, with different components specializing in different roles while maintaining their interdependence. These findings suggest that cooperation may be a fundamental feature of complex chemical systems, not an unusual or unlikely development. The community perspective also has profound implications for how we think about evolution and the nature of life itself. If life emerged from cooperation rather than competition, then collaboration and mutualism may be just as fundamental to biology as natural selection and survival of the fittest. This doesn't diminish the importance of competition in evolution, but it suggests that cooperation is an equally powerful and creative force in the history of life. In our quest to understand life's origins, we inevitably encounter the limits of knowledge and the boundaries of what can be definitively known. The events that gave rise to life occurred billions of years ago, under conditions that can only be approximated in modern laboratories, and they involved processes that may have left no direct trace in the geological or chemical record. This uncertainty can be frustrating for those who prefer clear answers and definitive explanations, but it can also be a source of wonder and inspiration. The uncertainty surrounding life's origins is not a failure of science, but a reflection of the profound nature of the questions we are asking. We are trying to understand one of the most remarkable transitions in the history of the universe, the emergence of self-organizing, self-reproducing, evolving systems from the non-living matter of early Earth. This transition involved processes that operated at the intersection of chemistry, physics, geology, and biology, creating emergent properties that were genuinely novel in the history of the cosmos. The fact that we don't have all the answers, that we may never have all the answers, doesn't diminish the value of the inquiry. Each new discovery, each refined hypothesis, each experimental result adds to our understanding and brings us closer to the truth, even if the complete truth remains elusive. The journey of discovery is itself valuable, regardless of whether we ever reach a final destination. Moreover, the uncertainty creates space for multiple approaches and perspectives, each contributing something valuable to our overall understanding. The metabolism-first theorists and the replication-first advocates, the RNA world enthusiasts, and the systems chemistry researchers all are exploring different aspects of the same fundamental mystery. Their debates and disagreements are not signs of failure, but evidence of a healthy, dynamic field of inquiry. The uncertainty also preserves a sense of mystery and wonder that might otherwise be lost if we had definitive answers to all our questions. There is something deeply moving about contemplating the emergence of life from non-life, something that touches on fundamental questions about the nature of existence and our place in the universe. This sense of wonder is not diminished by partial knowledge, it may actually be enhanced by it. Perhaps most importantly, the uncertainty reminds us that science is an ongoing human endeavor, not a completed catalogue of facts. Each generation of scientists brings new tools, new perspectives, and new insights to these ancient questions. The story we tell about life's origins today will undoubtedly be different from the story told by scientists 50 or 100 years from now. This is not a weakness, but a strength. It means that the questions remain alive and vital, still capable of surprising us and challenging our assumptions. The beauty of uncertainty lies not in the absence of knowledge, but in the presence of possibility. Each unanswered question is an invitation to explore, to hypothesize, to experiment, and to discover. The gaps in our understanding are not empty spaces, but fertile ground for new insights and revelations. In embracing this uncertainty, we embrace the very spirit of scientific inquiry that has brought us so far in understanding the natural world. The question of where life began is really multiple questions, each opening onto landscapes of possibility that are both scientifically rigorous and deeply poetic. The search for life's birthplace has taken scientists to some of the most extreme and beautiful environments on Earth, from the crushing depths of the ocean floor to the delicate interfaces between sea and sky. Each proposed origin site tells a different story about the conditions that might have nurtured the transition from chemistry to biology. The diversity of these origin stories reflects the complexity of life itself. There may not have been a single birthplace, but multiple laboratories where different aspects of biology were explored and refined. The chemistry of life may have been perfected in one environment, the first membranes in another, and the earliest forms of replication in yet another. These separate innovations may have been brought together by geological processes, creating the integrated systems we recognize as the first living things. What unites all these origin stories is their focus on boundaries and interfaces, places where different chemical environments meet and interact. Whether it's the boundary between water and rock at hydrothermal vents, the interface between sea and air in tidal pools, or the surface interactions between organic molecules and mineral crystals, life seems to emerge from the creative tension between different states of matter and different chemical regimes. These boundary environments are inherently dynamic, characterized by gradients of temperature, pressure, chemistry, and energy that create opportunities for complex molecular interactions. They are the chemical equivalent of ecological edge habitats, where the meeting of different environments creates unusual conditions that can support unique forms of organization and innovation. Deep beneath the ocean's surface, where sunlight never penetrates and pressures would crush any surface dweller, a different kind of energy drives one of Earth's most remarkable ecosystems. Here, at hydrothermal vents, superheated water rich in dissolved minerals erupts from the seafloor, creating underwater chimneys that reach toward the darkness above. These alien landscapes may represent our planet's earliest chemistry laboratories, places where the basic ingredients of life first learned to dance together in the deep. One of the most profound insights emerging from modern research into life's origins is that life may have been a community project from the very beginning. Rather than arising from a single self-replicating molecule or a single metabolic network, life may have emerged from the interactions and cooperation of multiple chemical systems, each contributing different capabilities to the emerging whole. This community perspective challenges the traditional image of early life as a solitary struggle for existence, a molecular battle of all against all, in which only the fittest survived. Instead, it suggests that cooperation and mutualism were fundamental features of life from its earliest stages. The first living systems may have been confederations of specialized components, each dependent on the others for survival and success. Evidence for this community model comes from several sources. Modern cells are themselves communities of cooperating molecular systems. Genetic replication machinery works together with metabolic networks, which work together with structural systems like membranes and cytoskeletons. None of these systems can function in isolation. They require the integrated cooperation of all the others. Even more striking is the fact that modern cells contain clear evidence of ancient community relationships. The organelles that power plant and animal cells, chloroplasts and mitochondria, are actually the descendants of bacteria that were incorporated into early eukaryotic cells billions of years ago. These organelles retain their own DNA and reproduce independently, yet they are fully integrated members of the cellular community. This arrangement, known as endosymbiosis, demonstrates that cooperation between different forms of life has been a major driver of evolutionary innovation. The community model also helps explain some of the chicken and egg problems that plague other theories of life's origins. If life emerged from the cooperation of multiple chemical systems, then there was no need for a single system to have all the capabilities of life from the beginning. One system might have specialized in information storage, another in catalysis, and another in maintaining boundaries and compartments. Each system could have been relatively simple, but their cooperation could have produced emergent properties that characterized life as a whole. This perspective also suggests that the search for life's origins should focus not just on individual molecules or reactions, but on the networks of interactions that could have given rise to biological organization. The key questions become: how do chemical systems learn to cooperate? What conditions favor the emergence of mutually beneficial relationships? How do networks of interacting systems develop the stability and complexity we associate with life? Recent research in systems chemistry and network theory is beginning to provide answers to these questions. Scientists have discovered that certain types of chemical networks naturally evolve cooperative relationships, with different components specializing in different roles while maintaining their interdependence. These findings suggest that cooperation may be a fundamental feature of complex chemical systems, not an unusual or unlikely development. The community perspective also has profound implications for how we think about evolution and the nature of life itself. If life emerged from cooperation rather than competition, then collaboration and mutualism may be just as fundamental to biology as natural selection and survival of the fittest. This doesn't diminish the importance of competition in evolution, but it suggests that cooperation is an equally powerful and creative force in the history of life. In our quest to understand life's origins, we inevitably encounter the limits of knowledge and the boundaries of what can be definitively known. The events that gave rise to life occurred billions of years ago under conditions that can only be approximated in modern laboratories, and they involve processes that may have left no direct trace in the geological or chemical record. This uncertainty can be frustrating for those who prefer clear answers and definitive explanations, but it can also be a source of wonder and inspiration. The uncertainty surrounding life's origins is not a failure of science, but a reflection of the profound nature of the questions we are asking. We are trying to understand one of the most remarkable transitions in the history of the universe, the emergence of self-organizing, self-reproducing, evolving systems from the non-living matter of early Earth. This transition involved processes that operated at the intersection of chemistry, physics, geology, and biology, creating emergent properties that were genuinely novel in the history of the cosmos. The fact that we don't have all the answers, that we may never have all the answers, doesn't diminish the value of the inquiry. Each new discovery, each refined hypothesis, each experimental result adds to our understanding and brings us closer to the truth, even if the complete truth remains elusive. The journey of discovery is itself valuable, regardless of whether we ever reach a final destination. Moreover, the uncertainty creates space for multiple approaches and perspectives, each contributing something valuable to our overall understanding. The metabolism-first theorists and the replication-first advocates, the RNA world enthusiasts and the systems chemistry researchers all are exploring different aspects of the same fundamental mystery. Their debates and disagreements are not signs of failure but evidence of a healthy, dynamic field of inquiry. The uncertainty also preserves a sense of mystery and wonder that might otherwise be lost if we had definitive answers to all our questions. There is something deeply moving about contemplating the emergence of life from non-life, something that touches on fundamental questions about the nature of existence and our place in the universe. This sense of wonder is not diminished by partial knowledge, it may actually be enhanced by it. Perhaps most importantly, the uncertainty reminds us that science is an ongoing human endeavor, not a completed catalogue of facts. Each generation of scientists brings new tools, new perspectives, and new insights to these ancient questions. The story we tell about life's origins today will undoubtedly be different from the story told by scientists 50 or 100 years from now. This is not a weakness, but a strength. It means that the questions remain alive and vital, still capable of surprising us and challenging our assumptions. The beauty of uncertainty lies not in the absence of knowledge, but in the presence of possibility. Each unanswered question is an invitation to explore, to hypothesize, to experiment, and to discover. The gaps in our understanding are not empty spaces but fertile ground for new insights and revelations. In embracing this uncertainty, we embrace the very spirit of scientific inquiry that has brought us so far in understanding the natural world. The question of where life began is really multiple questions, each opening onto landscapes of possibility that are both scientifically rigorous and deeply poetic. The search for life's birthplace has taken scientists to some of the most extreme and beautiful environments on Earth, from the crushing depths of the ocean floor to the delicate interfaces between sea and sky. Each proposed origin site tells a different story about the conditions that might have nurtured the transition from chemistry to biology. The diversity of these origin stories reflects the complexity of life itself, There may not have been a single birthplace, but multiple laboratories where different aspects of biology were explored and refined. The chemistry of life may have been perfected in one environment, the first membranes in another, and the earliest forms of replication in yet another. These separate innovations may have been brought together by geological processes, creating the integrated systems we recognize as the first living things. What unites all these origin stories is their focus on boundaries and interfaces, places where different chemical environments meet and interact. Whether it's the boundary between water and rock at hydrothermal vents, the interface between sea and air in tidal pools, or the surface interactions between organic molecules and mineral crystals, life seems to emerge from the creative tension between different states of matter and different chemical regimes. These boundary environments are inherently dynamic, characterized by gradients of temperature, pressure, chemistry, and energy that create opportunities for complex molecular interactions. They are the chemical equivalent of ecological edge habitats, where the meeting of different environments creates unusual conditions that can support unique forms of organization and innovation. Deep beneath the ocean's surface, where sunlight never penetrates and pressures would crush any surface dweller, a different kind of energy drives one of Earth's most remarkable ecosystems. Here, at hydrothermal vents, superheated water, rich in dissolved minerals, erupts from the sea floor, creating underwater chimneys that reach toward the darkness above. These alien landscapes may represent our planet's earliest chemistry laboratories, places where the basic ingredients of life first learned to dance together in the deep. The discovery of hydrothermal vent ecosystems in the 1972 revolutionized our understanding of life's possibilities. Here, in the absence of sunlight, entire ecosystems thrive on chemosynthesis, the process by which organisms extract energy from chemical reactions rather than photosynthesis. Giant tube worms, ghostly crabs, and clouds of bacteria create a living gallery around these underwater springs, demonstrating that life can flourish in conditions that would have been unimaginable to earlier generations of biologists. For scientists studying life's origins, hydrothermal vents offer several compelling advantages as potential birthplaces. First, they provide abundant chemical energy in the form of reduced compounds like hydrogen sulfide and methane, which can fuel metabolic processes without requiring the complex machinery of photosynthesis. This chemical energy would have been essential for early life, which lacked the sophisticated energy harvesting systems of modern organisms. Second, the mineral-rich environment around hydrothermal vents could have provided both catalytic surfaces and raw materials for early biochemistry. The metal sulfides that precipitate around these vents can catalyze many organic reactions, potentially serving as primitive enzymes that could have facilitated the formation of complex organic molecules. Iron-sulfur clusters, which are common around hydrothermal vents, are still found at the active sites of many modern enzymes, suggesting a possible evolutionary connection. Third, the temperature and pressure gradients around hydrothermal vents create microenvironments with different chemical properties, allowing for the concentration and organization of organic molecules. The interface between hot, mineral-rich vent water and cold seawater creates natural reaction chambers where different types of chemistry can occur simultaneously. The alkaline hydrothermal vents, which produce warm, highly basic water rather than the acidic, superheated fluids of black smokers, may be particularly promising as origin sites. These vents create natural proton gradients, differences in acidity that are remarkably similar to the gradients that modern cells use to generate ATP. This suggests that the basic energy metabolism of life may have evolved to take advantage of naturally occurring chemical gradients around alkaline vents. Recent laboratory experiments have shown that the conditions around hydrothermal vents can indeed promote the formation of complex organic molecules, including some of the building blocks of RNA and proteins. While these experiments don't prove that life originated at hydrothermal vents, they demonstrate that such environments could have supported the chemistry necessary for life's emergence. The poetry of the hydrothermal vent origin story lies in its imagery of birth from the depths, of life emerging from Earth's own creative fire. In these underwater cathedrals of stone and steam, chemistry becomes theatre, and the drama of early life plays out against a backdrop of mineral spires and dancing thermal plumes. It's a story that connects life's origins to the planet's geological heart, suggesting that biology and geology have been partners from the very beginning. At the other end of the environmental spectrum, from the crushing depths of hydrothermal vents The gentle rhythms of tidal pools offer another compelling setting for life's origins. These temporary lakes, created twice daily by the retreat of ocean waves, represent some of nature's most elegant chemistry laboratories, enclosed spaces where seawater can be concentrated, heated, mixed, and experimented with under the patient supervision of the sun and moon. The appeal of tidal pools as potential birthplaces for life lies in their unique combination of concentration and cycling. As seawater evaporates in these shallow basins, it leaves behind increasingly concentrated solutions of organic and inorganic compounds. These concentrated solutions can promote chemical reactions that would be impossible in the dilute conditions of the open ocean, creating opportunities for complex molecular interactions and the formation of larger, more organized structures. The daily cycle of filling and drying also creates opportunities for the repetition of chemical processes, a kind of natural PCR, polymerase chain reaction, that could amplify successful molecular innovations. Each tidal cycle brings fresh materials and energy, while allowing successful chemical systems to persist and potentially reproduce. This cycling between wet and dry conditions may have been crucial for the evolution of the first self-replicating systems. Modern tidal pools demonstrate the creative potential of these environments. They are among the most productive and diverse ecosystems on Earth, supporting complex communities of organisms that have adapted to the extreme conditions of temperature variation, salinity changes, and periodic desiccation. The organisms that thrive in these environments, from colorful algae to resilient invertebrates, showcase nature's ability to find opportunity in apparent adversity. The mineral content of tidal pools could also have played important roles in early biochemistry. As seawater evaporates, it deposits various salts and minerals that could have served as catalysts or templates for organic chemistry. Clay minerals, which often accumulate in tidal environments, have particularly interesting properties for promoting organic reactions and could have served as primitive genetic systems before the evolution of RNA and DNA. Recent research has shown that the wet-dry cycling characteristic of tidal environments can promote the formation of long chains of RNA and other organic polymers. The drying phase concentrates the starting materials and brings them into close contact, while the wetting phase provides the aqueous environment necessary for many biochemical reactions. This natural chemistry set could have been instrumental in the formation of the first complex organic molecules. The ultraviolet radiation present in shallow tidal pools, while potentially destructive to complex organic molecules, could also have provided energy for driving chemical reactions that would not occur spontaneously. UV light can break apart simple molecules and create reactive intermediates that can then combine in new ways, potentially leading to the formation of more complex structures. The tidal pool origin story has a gentler poetry than the dramatic thermal vents. It's a story of patient experimentation rather than violent transformation. In these shallow laboratories, life could have emerged through countless small experiments, each low tide offering new opportunities for molecular innovation. The rhythmic cycling of the tides becomes a heartbeat of creation, pulsing with the fundamental rhythms of Earth and Moon. Perhaps the most unlikely candidates for life's midwives are the humble clay minerals that form some of Earth's most common sediments. Yet these seemingly inert materials may have played crucial roles in life's origins, serving as templates, catalysts, and organizing surfaces that help transform simple organic molecules into the complex, organized systems we recognize as living. Clay minerals are not simple substances, but complex crystalline structures with remarkable properties. Their layered structure creates vast surface areas with precisely organized arrangements of atoms, providing templates that can guide the organization of organic molecules. Different types of clay have different surface properties, creating a diverse library of potential catalytic and organizing environments. The surface of clay minerals can concentrate organic molecules from dilute solutions, bringing reactive components into close proximity and increasing the likelihood of productive chemical interactions. This concentration effect is particularly important for understanding how complex biochemistry could have emerged from the dilute organic soup of early Earth's oceans. Clay surfaces essentially create microenvironments where the chemistry of life could have been explored and refined. Perhaps most remarkably, some clay minerals can catalyze the formation of RNA and other complex organic polymers from simple starting materials. In laboratory experiments, certain clays have been shown to promote the assembly of RNA chains, up to 50 nucleotides, long approaching the length necessary for catalytic activity. This suggests that clay surfaces could have served as primitive ribozyme factories, helping to create the first RNA enzymes that could catalyze their own replication. Clay minerals also have the ability to grow and reproduce their crystal structure, creating new surfaces with the same catalytic properties as the original. This mineral reproduction could have provided a primitive form of heredity, allowing successful catalytic environments to be replicated and spread. Some scientists have proposed that clay minerals might have constituted the first genetic system, with different clay compositions serving as different genes that could be selected and evolved. The interaction between organic molecules and clay surfaces could also have led to the first primitive metabolic networks. Different minerals catalyze different types of chemical reactions, and a mixture of clay minerals could have created an integrated network of chemical transformations, a primitive metabolism that could extract energy and materials from the environment and use them to build more complex structures. The transition from clay-based systems to fully organic life would have been gradual, with organic molecules gradually taking over the catalytic and organizational roles originally played by mineral surfaces. RNA molecules that could replicate themselves would have had advantages over static clay templates, leading to the eventual dominance of organic genetic systems. But the clay scaffolding may have been essential for getting organic life started. Recent discoveries of organic molecules in meteorites and comets suggest that the raw materials for life were abundant in the early solar system. Clay minerals could have served as the surfaces where these cosmic ingredients were organized and refined into the first living systems. The story becomes one of partnership between the inorganic and organic worlds, with mineral surfaces serving as the matchmakers that brought together the molecules of life. The clay origin story has its own quiet poetry. It's a tale of humble materials playing extraordinary roles, of the earth itself serving as midwife to the emergence of life. In this story, life doesn't emerge from dramatic events, but from the patient, careful organization of simple materials on mineral surfaces. It's a story that connects life's origins to the very rocks beneath our feet, suggesting that the boundary between living and non-living may be more permeable than we typically imagine. Each proposed origin site for life tells not just a scientific story but a poetic one, reflecting different aspects of the human imagination and our relationship. In our quest to understand life's origins, we find ourselves in the position of detectives examining suspects in an ancient case, one so old that most of the evidence has long since vanished. Yet the suspects remain, scattered across the tree of life, each carrying clues about the earliest chapters of biology's story. Some are still with us today, thriving in environments that echo the conditions of early Earth. Others exist only as genetic echoes, their presence inferred from the molecular signatures they left in their descendants. Together, they form a rogues gallery of early life, each with its own story to tell about the transition from chemistry to biology. In the deepest branches of life's family tree, beyond the divergence of bacteria, archaea, and eukaryotes, beyond the split between any two groups of organisms we know today, there lived a remarkable creature that scientists have come to know by the acronym LUCA, the last universal common ancestor. This organism holds a unique place in the history of life. It was not the first living thing, but it was the grandmother of everything that followed. LUCA represents a pivotal moment in early evolution, when the scattered experiments of primitive life finally converged on a design so successful that all subsequent life would be built upon its foundation. By the time LUCA emerged, life had already been experimenting for perhaps hundreds of millions of years, trying out different chemical strategies, different genetic systems, and different ways of organizing matter into living forms. Most of these early experiments ended in extinction, leaving no trace in the modern world. But LUCA's lineage survived and flourished, eventually giving rise to every bacterium, every archaean, every plant, animal, and fungus that has ever lived. What we know about LUCA comes not from fossils it lived too long ago and was too small to leave direct traces, but from comparative genetics. By examining the genes shared by all modern forms of life, scientists can reconstruct the molecular toolkit that LUCA must have possessed. This genetic archaeology reveals a surprisingly sophisticated organism, one that had already solved many of the fundamental challenges of living. LUCA had DNA, RNA, and proteins, suggesting that the transition from the hypothetical RNA world to the modern genetic system had already occurred. It possessed ribosomes for making proteins, indicating that the basic machinery of cellular manufacturing was already in place. It had enzymes for DNA replication and repair, showing that the challenge of maintaining genetic information across generations had been solved. In many ways, Luca was already recognizably modern in its basic biochemistry. Yet Luca lived in a world utterly unlike our own. The atmosphere contained virtually no oxygen, and the oceans were probably quite hot, perhaps as warm as 80 degrees Celsius, 176 degrees Fahrenheit, in some regions. This suggests that Luca was a thermophile, an organism that thrived at high temperatures. Its environment was likely rich in hydrogen gas and other reduced compounds that could serve as fuel for primitive metabolisms. It may have lived near hydrothermal vents or other volcanic features, where chemical energy was abundant and the conditions were suitable for early life. The fact that Luca was already so sophisticated tells us something important about the nature of early evolution. The transition from non-life to life was not a single dramatic event, but a long process of experimentation and refinement. By the time Luca appeared, life had already been through countless iterations, countless failures and successes. The molecular machinery we see in Luca represents the culmination of this long process of evolutionary engineering. Luca also marks the beginning of the great diversification that would eventually produce all known forms of life. Shortly after Luca's time, perhaps within a few 100 million years, life split into the three great domains that still organize the living world today: bacteria, archaea, and eukaryotes. Each of these lineages would go on to explore different aspects of what it means to be alive, from the metabolic virtuosity of bacteria to the architectural complexity of eukaryotic cells. Among the most remarkable organisms on Earth today are the archaea, a group of microbes so unusual that they weren't even recognized as a distinct form of life until the 1972nd. These ancient pioneers have mastered the art of living in places where nothing else can survive: boiling hot springs, acidic volcanic pools, salt lakes, so concentrated they would pickle any other form of life, and the crushing depths of the ocean floor. In their ability to thrive in extreme conditions, they may represent our best window into what the earliest life forms were like. The discovery of archaea revolutionized our understanding of life's diversity and origins. For most of the history of biology, scientists divided life into two categories: prokaryotes, bacteria, and eukaryotes, everything else. But molecular studies revealed that what had been lumped together as bacteria actually consisted of two fundamentally different groups. True bacteria formed one group, but the archaea represented an entirely separate branch of life, as different from bacteria as bacteria are from us. What makes archaea so special is their biochemistry, which differs from both bacteria and eukaryotes in fundamental ways. Their cell membranes are built from different types of lipids, assembled in ways that make them extraordinarily stable under extreme conditions. Their enzymes are engineered to function at temperatures that would denature the proteins of most other organisms. Their genetic machinery, while sharing some features with bacteria, has unique characteristics that set them apart. Many archaea are extremophiles, lovers of extreme conditions. Thermophiles thrive in near-boiling water, with some species holding the record for life at the highest temperatures, surviving in environments hotter than 120 degrees Celsius, 248 degrees Fahrenheit. Acidophiles live in conditions so acidic they would dissolve metal, while alkaliphiles prefer environments so basic they would strip the skin from any unwary visitor. Halophiles live in salt concentrations that would desiccate any other form of life, turning their surroundings into natural mummies. These extreme lifestyles aren't just biological curiosities, they may represent echoes of the conditions that prevailed when life first emerged. Early Earth was a much more hostile place than the modern world, with higher temperatures, different atmospheric chemistry, and more intense geological activity. The fact that archaea have retained the ability to thrive under these conditions suggests that they may be living fossils, preserving metabolic strategies that were essential for survival in life's earliest chapters. Some archaea are methanogens, organisms that produce methane as a byproduct of their metabolism. These microbes play crucial roles in modern ecosystems, from the digestive systems of ruminants to the sediments of wetlands, but they may also represent one of the most ancient forms of metabolism. The ability to extract energy from simple compounds like hydrogen and carbon dioxide may have been one of the first energy harvesting strategies developed by early life. Others are chemolithotrophs, organisms that derive energy from the oxidation of inorganic compounds like sulfur, iron, or ammonia. This metabolism allows them to live in environments devoid of organic nutrients, extracting energy directly from the chemical resources of their mineral environment. Such organisms could potentially survive on Mars or other planets, making them important subjects for astrobiology research. The archaeal approach to life demonstrates that biology is far more flexible and creative than we might imagine. Where we see impossible conditions, archaea see opportunities. Their existence expands our conception of what life can be and where it might exist. In studying these remarkable organisms, we glimpse not only the deep past of our own planet, but also the potential for life in the cosmos beyond Earth. If archaea are the extreme specialists of the microbial world, bacteria are its great innovators. Over billions of years, bacteria have invented most of the fundamental biochemical processes that power life on Earth. They pioneered photosynthesis, nitrogen fixation, and countless other metabolic pathways. They learned to swim, to sense their environment, to communicate with each other, and to form complex communities. In many ways, bacteria wrote the playbook for life that all other organisms would later follow. The most revolutionary bacterial innovation was oxygenic photosynthesis, the process of capturing sunlight and using it to split water molecules, releasing oxygen as a byproduct. This breakthrough, achieved by cyanobacteria sometime around 2.5 billion years ago, fundamentally transformed our planet. Before photosynthesis, Earth's atmosphere contained virtually no free oxygen. After its invention, oxygen began to accumulate, eventually reaching levels that could support the evolution of complex, oxygen-breathing organisms like ourselves. Cyanobacteria, often called blue-green algae, though they're not actually algae, were the artists who painted Earth's sky blue with oxygen. These remarkable organisms learned to harness the most abundant energy source in the solar system, sunlight, and use it to power their cellular processes. The oxygen they released as waste was initially toxic to most other forms of life, leading to what scientists call the Great Oxidation Event, a massive extinction that nearly ended life on Earth before it had really begun. But life, as always, proved remarkably adaptable. Some organisms learned to tolerate oxygen, while others evolved ways to use it as a powerful source of energy for their own metabolisms. The invention of aerobic respiration, the process of using oxygen to extract energy from organic molecules, provided organisms with access to far more energy than had ever been available before. This energy windfall made possible the evolution of larger, more complex organisms and ultimately led to the rich, diverse biosphere we see today. Bacteria also pioneered many other essential processes. Some learned to fix nitrogen, converting the inert nitrogen gas of the atmosphere into ammonia that other organisms could use to build proteins and nucleic acids. Without nitrogen fixation, the complex chemistry of life would be impossible, as nitrogen is an essential component of all biological molecules that store information or catalyze reactions. Other bacteria became the first organisms to form cooperative communities. Bacterial biofilms, organized communities of microbes embedded in protective matrices, demonstrate sophisticated collective behaviors that were probably among the first examples of multicellular cooperation. These bacterial cities can coordinate their activities, communicate through chemical signals, and even sacrifice individual members for the good of the community. The metabolic creativity of bacteria is truly astounding. Different species have learned to extract energy from virtually every available source: sunlight, organic molecules, hydrogen gas, sulfur compounds, iron, methane, and countless other substances. This metabolic diversity allows bacteria to colonize virtually every environment on Earth, from the scalding waters of hot springs to the frozen wastes of Antarctica, from the acidic drainage of mines to the alkaline conditions of soda lakes. Perhaps most remarkably, bacteria have maintained their innovative spirit throughout their long evolutionary history. Even today, they continue to evolve new capabilities, sometimes developing resistance to human antibiotics within just a few years of their introduction. Their genetic flexibility and rapid reproduction allow them to adapt to new challenges with a speed that larger, more complex organisms cannot match. In the shadowy borderlands between living and non-living exist some of the strangest entities in biology: viruses. These microscopic packages of genetic material wrapped in protein coats challenge our very definitions of life. They cannot reproduce on their own, cannot metabolize nutrients, cannot maintain homeostasis. Yet they evolve, they adapt, and they play crucial roles in the ecology of every known form of life. Whether viruses are alive, almost alive, or something else entirely remains one of the most fascinating puzzles in biology. Viruses exist in a state of suspended animation when outside their host cells. A virus particle, or virion, is essentially a microscopic message in a bottle, a bundle of genetic instructions, waiting for the right cellular machinery to read and execute them. Some viruses are so simple they contain only a few genes, while others rival small bacteria in their genetic complexity. But all viruses share the same basic strategy. They hijack the cellular machinery of their hosts to produce more viruses. The relationship between viruses and their hosts is often described as parasitic, and indeed many viruses cause disease and death. But the reality is more complex and nuanced. Viruses have been intimately involved in the evolution of life for billions of years, and their influence has not always been destructive. Some viruses carry genes from one host to another, facilitating horizontal gene transfer that can introduce beneficial innovations. Others appear to play regulatory roles, helping to control the populations of their hosts, or even providing beneficial functions. One of the most intriguing questions about viruses concerns their origins. Did they evolve from more complex, cellular organisms that gradually lost their independence? Are they descendants of the first self-replicating molecules that somehow never evolved cellular machinery? Or did they arise later, as escaped genetic elements from cellular organisms? Each hypothesis has its supporters and its challenges. The RNA world hypothesis suggests that viruses might be remnants of an ancient RNA-based world that preceded the evolution of DNA and proteins. Many viruses use RNA rather than DNA as their genetic material, and some RNA viruses have ribozymes, RNA molecules with catalytic activity that echo the hypothetical RNA organisms of life's earliest chapters. If this view is correct, then viruses might be among the most ancient forms of biological organization, predating not only their cellular hosts but the very concept of the cell itself. The idea that viruses might predate their hosts is particularly intriguing when we consider giant viruses recently discovered viral species that are larger and more complex than some bacteria. These viruses have hundreds of genes and sophisticated cellular machinery that seems almost too complex for simple parasites. Some scientists have proposed that giant viruses represent a fourth domain of life, as fundamental as bacteria, archaea, and eukaryotes. The genetic flexibility of viruses is extraordinary. They can evolve at rates that make bacterial evolution seem glacial, acquiring new genes, discarding old ones, and recombining their genetic material in ways that would be impossible for cellular organisms. This genetic promiscuity allows viruses to adapt rapidly to new hosts, to evade immune systems, and to explore evolutionary possibilities that are closed to more conventional forms of life. Perhaps the most beautiful aspect of viral biology is its strangeness, the way viruses challenge our assumptions about what life can be. They remind us that the universe of biological possibility is far stranger and more diverse than our limited experience would suggest. In their twilight existence between chemistry and biology, viruses embody the mystery and ambiguity that makes the study of life's origins so compelling. As we step back from our introduction to these candidates in life's origin story, we find ourselves in the presence of remarkable diversity. From Luca, the sophisticated ancestor that unified all subsequent life, to the archaea with their mastery of impossible environments, from the innovative bacteria that invented the fundamental processes of biology to the enigmatic viruses that challenge our very definitions of life, each tells us something different about the nature of biological possibility. Luca reminds us that even the earliest successful life was already complex and sophisticated, the product of millions of years of evolutionary experimentation. The archaea show us that life can thrive in conditions we would consider utterly hostile, expanding our understanding of where life might exist both on Earth and beyond. Bacteria demonstrate the power of innovation and adaptation, showing how simple organisms can develop solutions to virtually every challenge the environment can present. And viruses remind us that the boundary between living and non-living is far more permeable and mysterious than we might expect. Each of these candidates calls to different aspects of our imagination. Perhaps you're drawn to the pioneering spirit of the archaea, thriving in their extreme environments with a stubborn persistence that speaks to the resilience of life itself. Maybe you're fascinated by the creative energy of bacteria, constantly inventing new ways to make a living in an ever-changing world. Or perhaps you're intrigued by the enigmatic nature of viruses, existing in the spaces between our categories and definitions. The beauty of this diverse cast of characters is that they don't represent competing explanations for life's origins. They represent different chapters in the same grand story. Each has played its role in the emergence and evolution of life. Each has contributed something essential to the biological richness we see around us today. In studying them, we're not just learning about ancient history. We're discovering the fundamental principles that continue to govern life in all its myriad forms. As we continue our journey through the deep history of life, these candidates will serve as our guides, each offering insights into different aspects of what it means to be alive. They remind us that life's story is not a simple linear narrative, but a complex web of relationships, innovations, and possibilities that continues to unfold even today. In their diversity, we glimpse the creative power of evolution and the endless capacity of life to surprise, inspire, and humble us with its ingenuity. In any good detective story, there comes a moment when the investigator lays out the evidence, the fingerprints on the windowsill, the footprints in the garden, the witness accounts that suddenly align to reveal the truth. In our investigation of life's origins, we face a more challenging task. Our crime scene is billions of years old. Most of the evidence has been destroyed by time and geology, and the perpetrator we're seeking is not a who but a what, the mysterious transition from chemistry to biology that gave birth to everything we call alive. Yet clues remain, scattered across disciplines and encoded in everything from ancient rocks to modern genomes. These are our smoking guns, evidence so compelling that it forces us to reconsider what we thought we knew about life's beginnings. Some clues are written in stone, preserved as chemical signatures that have survived since Earth's youth. Others are embedded in the DNA of living organisms, molecular timepieces that tick backwards through deep time. Still others emerge from laboratories where scientists attempt to recreate the conditions and processes that might have given rise to the first living things. Each type of evidence tells a different part of the story, and none alone provides a complete picture. But together, they begin to sketch the outlines of one of the most remarkable events in the history of the universe, the moment when matter learned to organize itself into patterns that could persist, reproduce, and evolve. The evidence is sometimes contradictory, often incomplete, and always humbling in its reminder of how much we still don't know. But it is also beautiful, profound, and deeply moving in its testament to the creativity and persistence of life in the face of seemingly impossible odds. Long after the soft tissues of ancient organisms have decomposed, and even their cellular structures have been obliterated by geological processes, something more subtle often remains: their chemical fingerprints. These molecular traces, preserved in rocks that formed billions of years ago, provide some of our most compelling evidence for early life. They are like whispers from the deep past, faint but unmistakable signatures of biological processes that once transformed the chemistry of our planet. The most important of these chemical fossils involves the element carbon, which forms the backbone of all known life. Living organisms have a distinct preference for the lighter isotope of carbon, carbon-12, over its heavier cousin, carbon-13. This biological discrimination occurs because the enzymes that incorporate carbon into organic molecules work slightly more efficiently with the lighter isotope. The difference is small, only about 25 parts per thousand, but it's consistent and measurable, creating a distinctive isotopic signature that can persist in rocks for billions of years. When paleochemists analyze ancient sediments and find carbon with the depleted carbon-13 signature characteristic of biological processes, it's strong evidence that life was present when those rocks formed, even if no actual fossils can be found. This isotopic evidence has been crucial in pushing back the earliest evidence for life on Earth, providing hints of biological activity in rocks far older than any containing recognizable fossils. The interpretation of these isotopic signatures requires extraordinary care. Non-biological processes can sometimes produce similar isotopic patterns, and the signature can be altered by geological processes over billions of years. Scientists must consider alternative explanations, examine multiple samples, and look for supporting evidence before concluding that a particular isotopic signature represents ancient life. The work is painstaking and often controversial, but it has opened up entirely new ways of searching for life's earliest traces. Different types of organisms leave different chemical fingerprints, allowing scientists to infer not just that life was present, but what kinds of life were thriving. Methanogenic archaea, for example, produce organic compounds with extremely depleted carbon-13 signatures, much more extreme than those produced by other forms of life. When scientists find these signatures in ancient rocks, it suggests that methanogenic ecosystems, perhaps similar to those found around modern hydrothermal vents, were operating billions of years ago. Sulfur isotopes tell another part of the story. The way organisms process sulfur compounds creates characteristic isotopic signatures that can reveal information about ancient metabolisms and environmental conditions. Before about 2.4 billion years ago, sulfur isotope ratios in rocks show distinctive patterns that disappear from the geological record around the time of the Great Oxidation Event. This suggests that the rise of oxygen fundamentally changed sulfur cycling on Earth, providing an independent line of evidence for one of the most important transitions in our planet's history. Nitrogen isotopes add yet another layer to the story. The process of nitrogen fixation, the conversion of atmospheric nitrogen into ammonia that organisms can use, leaves characteristic isotopic signatures. Finding these signatures in ancient rocks suggests that the complex biochemistry necessary for nitrogen fixation had evolved by the time those rocks formed, providing insights into the sophistication of early metabolic networks. Other types of molecular fossils include complex organic compounds called biomarkers, molecules that are produced only by living organisms and can survive in rocks for billions of years. Steranes, derived from steroids, provide evidence for early eukaryotic life. Hopanes, derived from bacterial membrane lipids, reveal the presence of specific types of bacteria. These molecular fossils can sometimes provide more detailed information about ancient ecosystems than traditional fossils, revealing the presence of organisms that left no other trace in the rock record. The study of chemical fossils has also revealed evidence for some of life's most important innovations. The appearance of certain biomarkers in rocks around 2.7 billion years old provides evidence for the evolution of oxygenic photosynthesis, even in the absence of recognizable cyanobacterial fossils. Other chemical signatures suggest that complex cell membranes and sophisticated metabolic pathways had evolved much earlier than previously thought. Among the most ancient and controversial pieces of evidence for early life comes from a remote region of southwestern Greenland, where some of Earth's oldest rocks tell a story that may stretch back to within 800 million years of our planet's formation. Here, in the Isua supracrustal belt, metamorphic rocks that formed 3.8 billion years ago contain carbon isotope signatures that some scientists interpret as evidence of biological activity. These Greenlandic rocks are themselves remarkable survivors. They have endured nearly 4 billion years of geological upheaval, including multiple episodes of heating, compression, and chemical alteration that would have destroyed most traces of their original composition. That any evidence of ancient chemistry remains in these rocks is extraordinary. That this evidence might include signatures of life is almost miraculous. The carbon isotope ratios found in these rocks show the characteristic depletion in carbon-13 that is typically associated with biological processes. The signature is not as strong or as clear as in younger rocks, which could reflect either the alteration of the original signal by geological processes or differences in early metabolisms. But it is consistent with what we might expect from ancient biological activity, particularly from methanogenic organisms that produce extremely depleted carbon isotope signatures. The interpretation of these signals has been the subject of intense scientific debate. Critics argue that the isotopic signatures could have been produced by non-biological processes, or that they might represent contamination from younger organic matter. The metamorphic alteration that these rocks have undergone makes it difficult to determine their original composition with certainty, and the isotopic signatures are at the limits of what current analytical techniques can reliably measure. Supporters of the biological interpretation point out that the isotopic signatures are found in multiple samples from different locations within the rock formation, suggesting that they represent original features rather than contamination. They also note that the signatures are associated with carbon-rich layers that could represent ancient organic sediments, and that similar signatures in younger rocks are universally accepted as evidence of biological activity. Recent advances in analytical techniques have allowed scientists to examine these rocks with unprecedented precision, revealing additional details about their chemistry and structure. Some studies have found organic compounds that could be degraded remnants of biological molecules, while others have identified mineral textures that might represent fossilized microbial mats. However, each new analysis seems to raise as many questions as it answers, highlighting the challenges of interpreting evidence from such ancient and altered rocks. The Greenland rocks also preserve evidence of the environmental conditions that prevailed on early Earth. They formed in a world with virtually no oxygen in the atmosphere, where the oceans were probably quite warm and rich in dissolved minerals. Volcanic activity was much more intense than today, and the surface was bombarded by asteroids and comets. If life did exist at this time, it would have thrived in a world utterly unlike our own. Whether or not the Greenland rocks contain evidence of life, they provide a unique window into Earth's earliest history. They formed at a time when our planet was still settling into its current configuration, when the processes that would shape the evolution of life were just beginning to operate. In their ancient chemistry, we glimpse the conditions that set the stage for life's emergence, even if we cannot yet definitively say whether that emergence had already begun. The ongoing debate over the Greenland rocks illustrates both the promise and the challenges of using chemical fossils to study life's origins. These subtle signals push our analytical capabilities to their limits and force us to confront the fundamental question of how we recognize life in the absence of obvious biological structures. They remind us that the search for life's origins is not just a scientific endeavor, but a philosophical one, requiring us to define what we mean by life and what evidence we would accept for its presence. Hidden within the DNA of every living organism is a molecular timepiece that has been ticking steadily since life began. This biological clock doesn't measure seconds or minutes, but evolutionary time, the gradual accumulation of genetic changes that occurs as species diverge from their common ancestors. By reading these molecular clocks, scientists can estimate when different groups of organisms first appeared, pushing our understanding of life's timeline far back into the Precambrian depths. The principle behind molecular clocks is elegantly simple. As organisms evolve, their DNA accumulates mutations at roughly constant rates. These mutations are mostly neutral, they don't help or harm the organism, so they accumulate steadily over time like radioactive decay. By comparing the DNA sequences of different species and counting the number of differences between them, scientists can estimate how long ago those species shared a common ancestor. The molecular clock approach has revolutionized our understanding of evolutionary history. Unlike fossil-based studies, which are limited to organisms that happen to be preserved in rocks, molecular clocks can provide information about any group of living organisms, including those that rarely fossilize. This has been particularly valuable for studying microorganisms, which dominate life's diversity but have left relatively few fossils. The first step in using molecular clocks is choosing the right genes to analyze. Different genes evolve at different rates, so scientists must select genes that change slowly enough to provide reliable comparisons across billions of years, but quickly enough to accumulate measurable differences. Ribosomal RNA genes, which are essential for protein synthesis and therefore highly conserved, have been particularly useful for studying deep evolutionary relationships. Calibrating molecular clocks requires connecting genetic differences to actual time intervals, usually by using fossils of known age. For example, if scientists know that two groups of organisms diverged 500 million years ago based on fossil evidence, they can use the genetic differences between modern representatives of those groups to calculate the rate at which mutations accumulate. This calibrated rate can then be applied to other evolutionary divergences where fossil evidence is lacking. The results of molecular clock studies have been surprising and sometimes controversial. Many molecular clocks suggest that major groups of organisms are much older than their first appearance in the fossil record. For bacteria and archaea, molecular clocks point to origins that may extend back 4 billion years or more, approaching the very limits of when life could have existed on Earth. Perhaps most remarkably, molecular clocks suggest that the three great domains of life, bacteria, archaea, and eukaryotes diverged from each other very early in evolutionary history, possibly within the first billion years of life's existence. This implies that the fundamental architecture of life was established much earlier than previously thought, during a period when Earth was still a very different world from today. Molecular clocks have also provided insights into the timing of specific evolutionary innovations. The evolution of oxygenic photosynthesis, for example, appears to have occurred several hundred million years before oxygen began accumulating in the atmosphere, suggesting that this revolutionary biochemical process had a long incubation period before it transformed Earth's environment. The study of molecular evolution has revealed that different parts of the genome evolve at different rates, creating multiple clocks that can be used to study different timescales. Genes that are essential for basic cellular functions evolve very slowly and can be used to study the deepest splits in the tree of life. Genes that are less constrained by natural selection evolve more rapidly and can be used to study more recent evolutionary events. Recent advances in DNA sequencing technology have made it possible to analyze entire genomes rather than individual genes, providing much more data for molecular clock studies. Whole genome comparisons have revealed complex patterns of gene gain, loss, and horizontal transfer that complicate simple clock-like models of evolution but provide much richer information about evolutionary history. One of the most intriguing findings from molecular clock studies is the suggestion that life may have faced several major bottlenecks early in its history, periods when the diversity of life was drastically reduced, perhaps by asteroid impacts or extreme environmental changes. These bottlenecks may explain why certain groups of organisms appear to have diverged rapidly after long periods of apparent stasis. Perhaps the most direct approach to understanding life's origins is to try to recreate the process in the laboratory. For over half a century, scientists have been conducting experiments designed to simulate the conditions of early Earth and observe whether the chemistry of life can emerge spontaneously from simpler components. These experiments, sometimes called origins of life or prebiotic chemistry research, have provided crucial insights into the chemical pathways that might have led from non-living matter to the first primitive organisms. The most famous of these experiments was conducted by Stanley Miller and Harold Urey in 1953. Working at the University of Chicago, they created a closed system containing water, methane, ammonia, and hydrogen gases they believed were present in Earth's early atmosphere. They subjected this mixture to electrical sparks to simulate lightning, and after just 1 week, they found that complex organic molecules had formed, including several amino acids that are essential components of proteins. The Miller-Urey experiment was groundbreaking because it demonstrated that the building blocks of life could form spontaneously under conditions that might have existed on early Earth. The experiment captured the public imagination and launched the modern field of origins of life research. However, it also revealed the challenges of recreating billions of years of chemical evolution in a laboratory setting. Subsequent research has refined and expanded on Miller and Urey's original approach. Scientists have experimented with different atmospheric compositions, reflecting evolving ideas about the nature of Earth's early atmosphere. They have used different energy sources, including ultraviolet light, heat, and ionizing radiation. They have incorporated minerals and other environmental factors that might have influenced prebiotic chemistry. These experiments have succeeded in producing an impressive array of organic molecules, including amino acids, nucleotides, the building blocks of DNA and RNA, lipids, and even simple proteins and nucleic acids. Some experiments have created self-assembling vesicles that resemble primitive cell membranes, while others have produced RNA molecules with catalytic activity. Perhaps most remarkably, some experiments have created systems that exhibit primitive forms of evolution. RNA molecules that can replicate themselves, even imperfectly, can be subjected to artificial selection in the laboratory. Over many generations, these molecular populations can evolve improved replication abilities, better stability, or new catalytic functions. These directed evolution experiments provide insights into how complex biological functions might have emerged from simpler chemical systems. Modern origins of life research has moved beyond simple spark discharge experiments to explore more sophisticated scenarios for life's emergence. Some researchers are investigating the role of mineral surfaces in concentrating and organizing organic molecules. Others are studying the chemistry that occurs around hydrothermal vents, where hot, mineral-rich water provides both energy and catalytic surfaces for complex chemistry. The RNA world hypothesis has inspired numerous laboratory studies aimed at creating self-replicating RNA systems. These experiments have succeeded in creating RNA enzymes that can catalyze their own replication, though achieving truly autonomous self-replication remains elusive. The challenge is that RNA replication requires a complex molecular machinery that must itself be encoded by RNA, a chicken-and-egg problem that continues to challenge researchers. Recent experiments have also explored the possibility that life emerged from integrated networks of chemical reactions rather than from individual self-replicating molecules. These metabolism-first approaches attempt to create autocatalytic reaction networks, systems of chemical reactions that can maintain and reproduce themselves. Some of these experiments have created systems that can grow, reproduce their chemical organization, and even exhibit primitive forms of competition and selection. The integration of different approaches has led to increasingly sophisticated experimental systems. Some researchers are creating protocells, vesicles containing both genetic material and metabolic machinery that can grow, divide, and potentially evolve. These systems are still far from being truly alive, but they capture some of the essential features of living organisms and provide insights into how these features might have evolved. Laboratory genesis experiments have also revealed the importance of environmental factors in life's origins. The concentration of reactants, the pH of solutions, the presence of catalytic surfaces, and the cycling between different conditions all influence the chemistry that occurs. These findings suggest that life's emergence may have required very specific environmental conditions, perhaps occurring only in particular niches where multiple favorable factors converged. Despite their successes, laboratory experiments face fundamental limitations in recreating the origins of life. They operate over timescales of days to years, while the actual emergence of life may have taken millions or hundreds of millions of years. They typically focus on individual chemical processes, while life's emergence likely involved the integration of many different processes. Most importantly, they are conducted by intelligent scientists who design the experiments and interpret the results, while the original process had no designer or goal-directed guidance. As we survey the evidence for life's origins, the chemical fossils in ancient rocks, the molecular clocks ticking backwards through deep time, the laboratory experiments that recreate fragments of prebiotic chemistry, we must confront a humbling truth. Despite decades of research and remarkable scientific advances, we may never find the first creature or definitively identify the moment when chemistry became biology. This limitation is not a failure of science, but a reflection of the profound nature of the questions we are asking. The problem is partly temporal. The events we are trying to understand occurred billions of years ago, under conditions that can only be approximated in modern laboratories. The direct evidence for these events has been largely erased by geological processes, and what remains is often ambiguous and subject to multiple interpretations. We are like archaeologists trying to reconstruct a civilization from a few scattered artifacts, knowing that most of the evidence has been lost forever. But the problem is also conceptual. Life did not emerge in a single dramatic moment, like a switch being thrown or a spark igniting a fire. Instead, it was almost certainly a gradual process, a slow transition from simple chemical systems to more complex, integrated, and eventually self-reproducing networks. The boundary between non-life and life is blurry, and there may never have been a clear moment when that boundary was crossed. Life's origin may not trace back to a single event or first organism, but to a gradual emergence from networks of self-organizing chemical systems. Early Earth may have hosted many failed and successful experiments in biology, with only a few lineages surviving or merging through processes like gene transfer. Rather than frustrating, this uncertainty reveals the beauty of science, a continuous, collaborative journey toward understanding rather than final answers. Across disciplines, geochemistry, molecular biology, theoretical modeling, scientists contribute diverse insights that keep our understanding dynamic and evolving. Discoveries like ribozymes, the archaea domain, and organic molecules in space have repeatedly challenged assumptions, reminding us that life is adaptable, creative, and far from fully understood. Chemical fossils and lab simulations suggest that life likely arose through natural processes, with complexity gradually emerging from simplicity. We carry the legacy of those early beginnings. Mitochondria, genetic code, lipid membranes, all inherited from that ancient biochemical relay. Contemplating life's deep history shifts our perspective. We're not isolated anomalies in a meaningless universe, but expressions of a 4 billion-year journey, temporary stewards of an enduring biological spark. This awareness humbles and empowers us, framing our short lives as part of a far older and vaster story. The resilience of life, its ability to survive ice ages, asteroid impacts, and extinction events, shows that no single path defines it. Life's decentralized, experimental nature gives it strength and flexibility. This resilience offers hope. If life emerged here under harsh conditions, it could do so elsewhere too. Our understanding of Earth's origins informs our search beyond it. Mars, once warm and wet, may hold fossil traces of life. Europa and Enceladus hide vast oceans that could harbor microbial ecosystems. Even Titan, with its alien methane lakes, hints at the potential for entirely different life chemistries. As we expand our search, we broaden our definition of life. It may not require water or carbon. Silicon-based, plasma-based, or digital life emerging from information networks challenge our assumptions and expand what's possible. Life, at its core, may simply be complex pattern, maintenance, and information processing. Even if microbial life is common across the universe, the evolution of intelligent, technological civilizations may be rare. We might live in a galaxy filled with simple organisms, or one rich in sentient life we have yet to detect. We simply don't know, and that uncertainty is itself part of the wonder. This cosmic search returns us to Earth with deeper appreciation. The diverse life forms here, nautiluses, fungi, whales, are unique, irreplaceable expressions of evolution. Our role as conscious stewards matters because the life here is a singular experiment in the universe's creativity. Our search for the first life may never yield a single moment or organism we can point to as the beginning. The transition from chemistry to biology was likely gradual, scattered across time and place, leaving behind no singular fossil or footprint. But what it left is more powerful. Its echo in every living cell, every breath, every heartbeat. That first spark of life reverberates in bacterial mats that still thrive today, in the chemistry of deep-sea vents, and in the ancient metabolic rhythms within us. Though the first creature is long gone, it lives on through the patterns it created, shared genetic codes, membrane structures, and the core processes that power life. We are not just descended from that original organism, we are its continuation. There is something magical in emergence, how simple parts can give rise to something beautifully new. Billions of years ago, chemistry became biology. Over time, biology became consciousness. Now, you reading these words are the universe reflecting on itself. You are matter that has become mind. That ancient spark did more than replicate molecules. It began a process that would one day lead to wonder, empathy, and curiosity. The gift of life is also the gift of caring about our origins and of asking the questions that no other species has dared to ask. In tracing life's beginnings, we come to recognize ourselves not as observers but as participants in an ancient, ongoing story. We exist because life adapted, evolved, survived catastrophes, and passed its spark forward for billions of years. Every successful mutation, every evolutionary leap, every life form that endured hardships, it was all part of the long conversation that led to you. Even the simplest life forms from deep time like cyanobacteria oxygenating the atmosphere or eukaryotic cells joining forces set the stage for us. We carry in our bodies the elements forged in stars and the processes born in primordial seas. The very molecules that make you are ancient, arranged by a story that started long before you, but leads to you nonetheless. This journey reminds us that we are not separate from nature, we are nature, become aware of itself. Every breath you take, every thought you think, continues a story that began when the earth was young. Our lives are brief chapters in a vast book, but they are part of the same narrative that began with Luca, with Archaea, with life's first tentative steps. In seeking the first life, we discovered something profound, ourselves. We are the voice of that first creature now capable of wonder. The universe, through us, knows its own history and finds it beautiful. You are the dream of that first spark, made real. You are life celebrating itself.